Imagine everything you know about the universe. The planets, the stars, the galaxies. Now, this may seem like everything there is, but in reality, we have not even scratched the surface. Join us as we go on a journey to explore what truly lies beyond our universe. Diving into the origins of our universe, we confront one of the most mystifying questions that has baffled scientists for centuries. What caused the Big Bang? This momentous event, occurring around 13.8 billion years ago, marked the beginning of everything we know, from the tiniest particles to the vast galaxies. While the specifics of what triggered the Big Bang remain elusive, leading theories propose that it could have resulted from quantum fluctuations in a tiny, hot, and dense singularity. This singularity, defying our current understanding of physics, seemingly contained all the mass and energy of the cosmos. According to quantum theory, even in a vacuum state where no particles exist, there is still energy and temporary particles popping in and out of existence due to quantum fluctuations. Extrapolating from this theory, it's posited that such fluctuations could have sparked the incredible expansion of this singularity, birthing the universe as we know it. However, it's important to note that these hypotheses reside at the cutting edge of physics, intertwining quantum mechanics and general relativity, realms that scientists are still striving to unify. The mystery of the Big Bang's cause highlights not just our quest for knowledge, but also the incredible complexity and wonder of the universe. While the Big Bang theory is the most widely accepted explanation for the origin and evolution of the universe, there are indeed alternative theories that some scientists explore. One of the most intriguing is the steady-state theory. This theory posits that the universe doesn't have a beginning or an end in time. Instead, it maintains a constant average density despite its expansion. This is postulated to occur through the continuous creation of matter throughout the universe, making it look the same at any point in time. The steady-state theory, proposed in the late 1940s, offered explanations for the universe's expansion without requiring a singular creation event like the Big Bang. However, the discovery of the cosmic microwave background radiation in 1965 provided strong evidence for the Big Bang theory, leading to the decline in the popularity of the steady-state theory among scientists. Despite this, the steady-state theory remains an important part of the history of cosmology, demonstrating the evolving knowledge and understanding within the scientific community. It also serves as a reminder of the openness of science to different hypotheses and the continuous quest for understanding the mysteries of the universe. Additionally, theories such as the cyclic model, which suggests the universe undergoes endless cycles of expansion and contraction, continue to be explored and developed, adding richness and diversity to our understanding of cosmic origins. The question of what existed before the Big Bang plunges into the enigmatic depths of cosmological speculation, stretching the limits of our understanding about the universe and the laws of physics. Traditionally, the Big Bang theory, which describes the expansion of the universe from a singular, incredibly dense and hot state, doesn't provide answers about what came before it. This is because, according to the theory, time itself, along with space, matter, and energy, originated at the moment of the Big Bang. However, some theoretical physicists have ventured into the realms of what might have been before this event. One intriguing hypothesis suggests that the universe could have been undergoing a cycle of contraction and expansion known as the Big Bounce. According to this model, what we know as the Big Bang might have been the latest of many such bounces in an eternal cycle of cosmic rebirths. Another speculative scenario is the concept of a multiverse, proposing that our universe is just one of many universes, each with its own set of physical laws and constants. In this model, what existed before our Big Bang could potentially be another universe entirely. These inquiries push the boundaries of physics as we know it, venturing into the speculative and the untestable. The theories rely on advanced concepts in quantum physics and the still theoretical realm of quantum gravity, aiming to bridge the gap between quantum mechanics and general relativity. While these pioneering ideas offer tantalizing glimpses into pre-Big Bang cosmology, they remain largely in the realm of theoretical physics, underscoring the profound mystery of our universe's origins. The ultimate fate of the universe is a fascinating question that hinges on the nature of its expansion and the properties of dark energy, an elusive force that seems to be accelerating this expansion. Three prominent hypotheses predict vastly different endings: the Big Freeze, the Big Rip, and the Big Crunch. The Big Freeze scenario emerges from the concept that the universe will continue expanding indefinitely. As it does so, galaxies will move further apart, stars will burn out, and the universe will gradually cool as it heads towards a state of maximum entropy or disorder. This scenario suggests a lonely, cold end, trillions of years in the future, where the cosmos is dispersed into a near absolute zero wasteland. In contrast, the Big Rip theory takes the idea of an accelerating universe to a dramatic conclusion. Here, dark energy's repulsive force grows stronger over time, eventually overcoming all other forces, including gravity and electromagnetism. In such a scenario, galaxies, stars, planets, and eventually atoms themselves would be torn apart in a finite time, leading to a universe that rips itself to pieces. On the other hand, the Big Crunch proposes a reversal of the universe's expansion. If the density of the universe is high enough, gravitational forces could eventually halt and reverse the expansion, causing everything in the universe to collapse back into a hot, dense state, possibly setting the stage for another Big Bang. Current observations, particularly of the cosmic microwave background and the behavior of distant supernovae, suggest that the universe's expansion is accelerating, making the Big Freeze or the Big Rip the more likely outcomes. However, our understanding of dark energy is still in its infancy, and many questions remain unanswered. The universe's fate depends on the precise properties of dark energy, which physicists are ardently studying. As it stands, the cosmos keeps its ultimate fate a closely guarded secret, at least for now. The concept of cyclic universes, a sophisticated hypothesis that suggests an eternal series of universes each beginning with a Big Bang and ending in a Big Crunch, fundamentally challenges our traditional notions of cosmic beginnings and endings. In this model, each successive universe emerges from the collapse of the previous one, potentially solving the mystery of what existed before the Big Bang by proposing that it was simply another cosmic epoch. This cyclic pattern implies no true beginning or end, but rather an infinite sequence of dynamic cosmic life cycles. This perspective dramatically alters our understanding of time and the universe's permanence. Instead of viewing the Big Bang as a singular event marking the universe's birth, it becomes just one phase in an ongoing cosmic process. Such an idea challenges the linear progression of time and the universe's history as we understand it, suggesting that the cosmos may be far more dynamic and cyclic than previously conceived. Furthermore, cyclic universe models often incorporate insights from quantum physics and theories of quantum gravity, aiming to seamlessly bridge the divide between the physics of the very large, general relativity, and the very small, quantum mechanics. This interplay stands to not only redefine our comprehension of the universe's life cycle, but also push the boundaries of physics, inspiring new theories that could more completely unite these fundamental forces of nature. In essence, the notion of cyclic universes expands our conceptual horizons, inviting us to consider a cosmos where beginnings and endings are fluid, interconnected, and perennially reborn from the ashes of their predecessors. Such a universe defies our traditional understandings, challenging us to rethink our place within a much larger, possibly infinite cosmic continuum. Cosmic inflation, a theory proposed in the early 1980s by physicist Alan Guth, revolutionized our understanding of the early universe's evolution. This theory posits a brief period of exponential expansion that occurred a fraction of a second after the Big Bang, during which the universe's size increased by a staggering factor, possibly greater than 10 circumflex, 26 star. This rapid expansion is significant for several reasons. Firstly, cosmic inflation helps explain the remarkable homogeneity of the universe. Despite its vast size, the cosmic microwave background radiation, relic radiation from the early universe, is strikingly uniform everywhere we look. Inflation stretches out any initial irregularities, leading to a smoother, more uniform universe at large scales, consistent with our observations. Secondly, inflation addresses the horizon problem. This problem arises from the observation that regions of the universe billions of light-years apart have nearly identical temperatures, but would not have had enough time to come into thermal equilibrium with each other since the beginning of the universe. Inflation solves this by positing that these regions were once much closer before the exponential expansion, allowing them to thermally equilibrate. Moreover, inflation provides a mechanism for the generation of the primordial fluctuations that would eventually grow into the large-scale structures we observe in the universe today, such as galaxies and galaxy clusters. These fluctuations are thought to arise from quantum fluctuations in the early universe that were expanded to macroscopic scales by inflation. The nature and behavior of dark energy are among the most intriguing mysteries in modern cosmology. Currently prevailing as the dominant force driving the accelerated expansion of the universe, dark energy's constancy or variability over time remains a subject of active research and debate. Should dark energy change over time, either growing stronger or weaker, it would have profound implications for the ultimate fate of the universe. If dark energy were to increase in strength over time, this could lead to a scenario resembling the Big Rip. In this extreme future, the fabric of space itself would tear apart, with galaxies, stars, planets, and eventually atoms being ripped asunder by the ever-increasing repulsive force of dark energy. Such a universe would end not with a whimper, but with a catastrophic unraveling of everything that exists. Conversely, if dark energy were to weaken over time, the expansion of the universe might slow, halt, or even reverse. A weakening of dark energy could potentially lead to a scenario where gravitational forces retake dominance, culminating in a big crunch. This scenario envisions a universe that eventually collapses back on itself, potentially leading to conditions akin to those at the universe's birth, highly dense and hot, possibly even setting the stage for another Big Bang. Alternatively, if dark energy remains constant, as it seems to have over the observable past, the universe would continue its accelerated expansion, leading to the Big Freeze, where galaxies drift apart, stars burn out, and the universe gradually nears absolute zero temperature. The key to understanding dark energy and its implications lies in improved observational data and theoretical models. Upcoming observations from telescopes and space missions designed to probe the expansion history of the universe may offer new insights into the behavior of dark energy. Whether it proves to be a constant force, diminishes or grows over time, unraveling the mystery of dark energy is pivotal in predicting the universe's ultimate fate and understanding the fundamental laws that govern its expansion. The theory of quantum gravity represents an ambitious endeavor to reconcile the principles of quantum mechanics, which govern the subatomic world, with general relativity, which describes the gravitational force on a cosmic scale. As these two theories currently stand, they offer incompatible descriptions of the universe, particularly at the Planck scale, the smallest scale of space and time where the effects of gravity are thought to be governed by quantum mechanics. Quantum gravity aims to pave a unified path that could explain the universe's very beginning, an era where the conventional laws of physics break down. At the heart of this pursuit is the quest to understand the conditions of the universe at the moment of the Big Bang, and possibly what preceded it. Traditional physics cannot adequately describe such conditions where densities and temperatures reach infinitesimal points known as singularities. The theory of quantum gravity proposes that by applying quantum principles to gravity, it could smooth out these singularities, suggesting that the universe did not emerge from a point of infinite density. Instead, it may have had a finite, comprehensible state governed by quantum laws. One compelling offshoot of quantum gravity is the concept of a quantum bounce. This idea proposes that the universe we observe, which is currently expanding following the Big Bang, might have originated from the collapse of a previous universe. Instead of reaching a singular point of infinite density, quantum gravitational effects would cause the universe to bounce back, expanding anew. This cyclical process could imply an eternal succession of universes, each birthing from the ashes of its predecessor. By attempting to provide a framework through which the earliest moments of the universe can be understood, quantum gravity not only seeks to narrate the universe's origin, but also challenges our very concept of space, time, and the nature of reality. While still largely theoretical and facing significant hurdles in terms of empirical validation, advancements in this field have the potential to unlock answers to some of the most profound questions about the universe's inception and fundamental structure. A universe with no beginning or end, a concept that challenges our traditional views of linear time and progression, carries profound implications for both the nature of the cosmos and our philosophical understanding of existence. This idea, which aligns with certain cyclic or eternal universe models, suggests that the universe undergoes an infinite series of expansions and contractions or exists in a perpetual state without initiation or conclusion. Scientifically, this concept prompts a re-evaluation of the laws of physics as we know them. It implies that the singularity from which the universe is thought to have sprung in the Big Bang model might not represent the origin point of everything. Instead, singularities could be phases the universe passes through, with quantum gravity potentially governing these transitions. This challenges the notion of time as a linear arrow and suggests a cosmos where time is cyclical or perhaps even an illusion. Philosophically and existentially, a universe with no beginning or end evokes questions about the nature of our existence and the universe itself. It confronts us with a cosmos that is self-sustaining and eternal, eliminating the need for a creation event. This has implications for metaphysical debates about why there is something rather than nothing and the nature of cause and effect. The cosmic microwave background is a relic of the early universe, existing as a faint glow permeating the cosmos, offering a snapshot of the universe when it was just about 380,000 years old. This ancient light holds profound mysteries about the universe's infancy, its subsequent evolution, and the fundamental physics governing all matter and energy. Firstly, the uniformity of the CMB, with its temperature being incredibly consistent across the sky, reveals the universe's homogeneous nature at early times, yet it also poses the horizon problem. This uniformity raises questions about how regions of the universe, now billions of light-years apart, were once in thermal equilibrium without enough time to interact. This mystery points toward the concept of inflation, a rapid expansion of the universe that could explain the CMB's uniformity. Moreover, the slight temperature variations within the CMB, as minute as 1 part in 100,000, hold clues about the early distribution of matter and the seeds of cosmic structure. These fluctuations provide a foundation for understanding how galaxies and clusters formed over billions of years from initially small quantum fluctuations. Analyzing these temperature anisotropies has enabled scientists to determine the universe's age, geometry, and composition, including the puzzling dark matter and dark energy that make up most of the cosmos. The polarization of the CMB light, a more subtle feature, offers insights into the universe's first moments and the potential for gravitational waves generated during inflation. This could open a window into studying quantum gravity and understanding how the large-scale structure of the universe originated from the interplay between quantum mechanics and general relativity. Finally, the CMB challenges us to consider the existence of features that don't align with the predictions of the standard model of cosmology, such as the cold spot anomaly. These features spark ongoing investigation and debate, hinting that our understanding of the cosmos is still incomplete. In essence, the cosmic microwave background serves as a cosmic time capsule, encoding mysteries about the universe's birth, its accelerated expansion, and the intricate dance of matter and energy that followed. Unraveling these enigmas not only deepens our knowledge of the cosmos, but also propels forward the frontiers of physics, urging us to ponder fundamental questions about the nature of reality. Dark matter, the invisible substance thought to make up about 27% of the universe's total mass and energy, remains one of the most profound mysteries in modern astrophysics. Its presence is inferred from gravitational effects on visible matter, such as stars and galaxies, and on the cosmic microwave background, but it has not been directly detected. Several leading theories propose different candidates for what dark matter could be. One of the primary contenders is the weakly interacting massive particles, WIMPs. WIMPs are hypothetical particles that, as their name suggests, interact very weakly with ordinary matter, except through gravity. Their speculated existence springs from theories that go beyond the standard model of particle physics, such as supersymmetry. The appeal of WIMPs lies in their ability to naturally arise from these new physical theories, potentially explaining dark matter while also fitting well with the observed phenomena at the galactic scale. Another significant theory suggests that dark matter could be composed of axions. Axions are theoretical particles that are much lighter than WIMPs and were initially proposed to solve the strong CP problem in quantum chromodynamics. Unlike WIMPs, Axions would have extremely weak interactions with electromagnetic fields, making them another candidate for dark matter that would be difficult to detect but could permeate the universe in vast quantities. Sterile neutrinos represent another possibility. These are hypothesized versions of neutrinos that do not interact via the weak force, unlike the three known types of neutrinos in the standard model, making them sterile. Their existence could offer an explanation for dark matter, while also potentially addressing anomalies in neutrino mass observations. Moreover, there are more theoretical and exotic candidates such as primordial black holes and dark photons, suggesting a broader spectrum of possibilities that could account for dark matter. Primordial black holes are hypothetical small-scale black holes formed in the high-density conditions of the early universe, while dark photons are hypothetical particles that would mediate interactions within a dark sector, analogous to how photons mediate electromagnetic interactions. Each of these theories brings its own set of implications for the nature of dark matter and the broader laws of physics, pushing the boundaries of current scientific understanding. Future experiments and observations, such as those conducted with particle accelerators, telescopes, and cosmic surveys, aim to test these theories, potentially unveiling the true nature of dark matter and shedding light on one of the cosmos's most enigmatic constituents. The direct detection of dark matter has proven to be exceptionally challenging due to the very nature of what it is theorized to be, matter that does not interact with electromagnetic forces in any significant way. This means that dark matter does not absorb, emit, or reflect light, making it invisible and undetectable with conventional optical instruments. Its presence is inferred through gravitational effects on visible matter, such as the rotation rates of galaxies and the bending of light, gravitational lensing, around massive objects. The leading candidates for dark matter, such as weakly interacting massive particles, WIMPs, axions, and sterile neutrinos, interact with ordinary matter only through gravity or extremely weakly through other forces, if at all. This makes them incredibly difficult to detect with the equipment and methods developed to observe and measure particles that interact electromagnetically. For a WIMP or axion to be detected, it must collide with a nucleus in a detector in just the right way to leave an observable signal. The expected rate of such interactions is extremely low, meaning that detectors need to be incredibly sensitive and shielded from other sources of particles, such as cosmic rays, to avoid false signals. The theoretical models proposing the existence of these particles stretch beyond the standard model of particle physics, entering realms of physics that we are only beginning to probe. The parameters defining these particles, such as their masses and interaction strengths with ordinary matter, are largely unknown, requiring searches over a broad range of possible values. This uncertainty complicates the search, as experiments must be designed to be sensitive to a wide range of potential signals. Advanced experiments designed to directly detect dark matter are typically placed deep underground or underwater to shield them from cosmic rays and other background noise that could mimic or obscure the signals from dark matter particles. These experiments use a variety of detection methods and materials in the hope of capturing an interaction between a dark matter particle and ordinary matter. Despite the lack of direct detection thus far, these efforts have significantly constrained the properties of dark matter candidates, narrowing the search and refining our understanding of what dark matter could be. In essence, the elusive nature of dark matter is a reflection of its unique properties, interacting weakly, if at all, with the forces that govern everyday matter. This challenges scientists to develop increasingly innovative and precise detection methods, pushing the frontiers of technology and theoretical physics in the quest to uncover the universe's dark secrets. Dark energy is thought to be the mysterious driving force behind the accelerating expansion of the universe, a phenomenon that defies the expected gravitational pull that should be slowing the expansion down. Discovered through observations of distant supernovae in the late 1990s, the acceleration suggests that the fabric of the cosmos is being stretched out, growing larger at an ever-increasing rate. The precise nature of dark energy remains one of the greatest puzzles in cosmology, but it is broadly characterized as a form of energy that permeates all of space, exerting a repulsive force which opposes the force of gravity. This repulsive force is what contributes to the accelerated expansion of the universe. There are a few leading theories about its nature. 1. Cosmological constant. Proposed by Albert Einstein as part of his theory of general relativity, the cosmological constant, lambda, represents a constant energy density filling space homogeneously. Einstein originally introduced it to allow for a static universe, but it has been repurposed to explain acceleration. In this scenario, dark energy is constant and unchanging, providing a steady push that accelerates the universe's expansion. 2. Quintessence. Unlike the cosmological constant, quintessence involves a dynamic, evolving field that changes over time and space. This field would have energy properties that could vary, leading to periods of acceleration and possibly deceleration throughout the history of the universe. Quintessence introduces a level of complexity, suggesting that the strength of dark energy is not constant, but can change, impacting how and at what rate the universe expands. Regardless of its exact nature, the contribution of dark energy to the accelerating expansion has profound implications for the fate of the universe. It suggests a future where galaxies drift ever further apart, potentially leading to a cold, isolated cosmos. Current research aims to measure the properties of dark energy more precisely, using observations from telescopes and cosmic surveys to understand how it has shaped the evolution of the universe from the Big Bang to the present day. Understanding dark energy and its contribution to cosmic acceleration not only deepens our knowledge of the universe's destiny, but also challenges our understanding of physics, pushing scientists to refine or even rethink our theories of the cosmos. To unravel the enigmas of dark matter and dark energy, scientists have embarked on a variety of ambitious experiments and observational programs. These efforts include both earthbound and space-based approaches designed to probe different aspects of these mysterious components of the universe. Facilities like the Large Underground Xenon (LUX) experiment and its successor, the Lux Zeppelin (LZ) experiment, play a crucial role in the direct detection of dark matter. Located deep underground to avoid cosmic rays and other background radiation, these experiments aim to catch the rare interactions between dark matter and normal matter. Complementing these are indirect detection projects such as the Fermi Large Area Telescope (LAT) and the Alpha Magnetic Spectrometer (AMS-02) aboard the International Space Station, which search for cosmic rays or gamma rays that might emerge from dark matter particles annihilating or decaying in space. Meanwhile, particle colliders like the Large Hadron Collider (LHC) at CERN are on a quest to create dark matter particles during high-energy particle collisions, providing a direct avenue to study their properties. Turning to dark energy, the Dark Energy Survey (DS) utilizes a 570-megapixel camera mounted on a telescope in Chile to observe galaxies and supernovae across a vast swath of the sky. The goal is to gauge how dark energy influences cosmic expansion and the growth of large-scale structures over time. Alongside DES, the Euclid mission, an initiative of the European Space Agency (ESA), map the geometry of the dark universe. By measuring galaxy redshifts and the bending of light due to gravitational lensing, Euclid hopes to shed light on dark energy's role in the expanding cosmos. Further expanding our observational capacity, the Vera C. Rubin Observatory Legacy Survey of Space and Time (LSST) will execute a decade-long survey, delivering detailed and frequent images of the entire sky. This colossal dataset will prove invaluable not just for studying dark energy, but also for exploring dark matter by tracking how billions of galaxies and cosmic structures evolve over time. These experiments and missions collectively represent a significant portion of the global effort to decipher dark matter and dark energy. Through a blend of direct detection, indirect observation, and advanced simulations, scientists are peeling back the layers of mystery that cloak these dark components, edging closer to a comprehensive understanding of the cosmos. In the vast expanse of the cosmos, the mysteries of dark matter and dark energy hold a place of prominence, compelling scientists to ponder over alternative explanations to these enigmatic forces. Despite accounting for about 95% of the universe, dark matter and dark energy elude direct detection, existing more as theoretical constructs than observable phenomena. One intriguing proposal posits that instead of attributing the accelerated expansion of the universe to dark energy, modifications to Newton's law of gravitation on cosmic scales could provide an alternative explanation. This theory, known as modified Newtonian dynamics (MOND), suggests adjustments to the gravitational force equation at very low accelerations, such as those found on galactic outskirts, could eliminate the need for dark matter. Similarly, theories like the emergent gravity propose that the effects attributed to dark matter are instead the result of the quantum vacuum's influence on gravity. These alternative theories challenge the dark matter and dark energy paradigms, inviting a closer examination of our universe's fundamental laws. While these explanations remain speculative, their exploration enriches our understanding of the cosmos, encouraging a re-evaluation of the very fabric of reality. Dark matter and energy are the architects of the universe, shaping its structure and evolution in profound ways. Despite their elusive nature, their presence is inferred through the gravitational influence they exert on visible matter. Dark matter, an invisible substance, forms a cosmic scaffolding on which galaxies and clusters of galaxies are built. It acts like the glue that holds these structures together, preventing them from being torn apart by their own rotational movement. Without dark matter, the gravitational force observed within galaxies would not be sufficient to keep them intact based on the visible matter alone. On the other hand, dark energy acts as a mysterious force that is driving the universe to expand at an accelerating rate. It counters the effects of gravity and is thought to permeate all of space, pushing galaxies away from each other. This accelerated expansion influenced by dark energy means that the universe is growing larger every moment, creating an ever-expanding cosmic landscape. The interplay between the attractive force of dark matter and the repulsive push of dark energy has led to the formation of the vast cosmic web, a complex network of interconnected filaments of galaxies separated by giant voids. This delicate balance between dark matter and energy not only dictates the large-scale structure of the universe, but also determines its ultimate fate. The discovery of dark matter particles would signify a monumental breakthrough in physics, heralding a new era of understanding the universe's most fundamental constituents. Currently, dark matter remains one of the most tantalizing mysteries, an unseen force inferred only through its gravitational effects on visible matter. Its direct detection would provide empirical evidence supporting its existence, moving it from the realm of theoretical physics into the tangible universe. This would not only validate decades of astrophysical research and observations, but also expand the standard model of particle physics, which currently does not accommodate dark matter. Unveiling the nature of dark matter particles could lead to a deeper comprehension of the forces that govern the universe, possibly uncovering new physics beyond our current theoretical frameworks. It might pave the way for unified theories that reconcile quantum mechanics with general relativity, offering insights into the earliest moments after the Big Bang and revealing the mechanisms behind galaxy formation and evolution. Furthermore, understanding dark matter could have profound implications for technologies dependent on fundamental physics, potentially leading to advancements in fields as diverse as quantum computing, energy generation, and materials science. In essence, the discovery of dark matter particles would be a cornerstone in the quest for a comprehensive understanding of the cosmos, reshaping our knowledge of the universe and our place within it. The elusive nature of dark matter and energy means that there may indeed be observable effects or signatures that have thus far gone undetected or misinterpreted within the cosmic tapestry. Given that dark matter does not emit, absorb, or reflect light, its presence is inferred primarily through gravitational effects on visible matter, such as the rotation curves of galaxies and gravitational lensing. Meanwhile, dark energy's influence is perceived through the accelerated expansion of the universe. However, these known phenomena might only be the tip of the iceberg regarding how dark matter and energy interact with the observable universe. Astrophysicists continually refine their instruments and methodologies, hoping to uncover subtle cues that have been overlooked. For instance, anomalies in the cosmic microwave background, radiation, or irregularities in the distribution of galaxies could hint at previously unrecognized influences of dark matter and energy. Additionally, advanced simulations of the universe's evolution incorporating dark matter and energy might reveal discrepancies with observations, suggesting alternative behaviors or interactions. The James Webb Space Telescope, with its unprecedented sensitivity and resolution, could detect faint signatures that hint at the dynamics of dark matter and energy within the early universe. Ultimately, identifying these missing observable effects would necessitate a combination of innovative technology, novel theoretical frameworks, and perhaps a bit of serendipity. Any new findings could significantly alter our understanding of the universe's composition and evolution, offering fresh insights into the fundamental laws of physics. Galactic phenomena have posed intriguing challenges to our understanding of dark matter, often forcing scientists to reassess their theories about this mysterious component of the universe. One of the most compelling puzzles is the discrepancy between the predicted distribution of dark matter in galaxies based on simulations and what is observed through astrophysical measurements. According to the prevailing cold dark matter model, dark matter should be densely packed at the centers of galaxies, forming a steep cusp. However, observations of the rotational speeds of stars and gas in many galaxies suggest a much flatter distribution, known as a core. This cusp core problem raises questions about the nature of dark matter and the processes involved in galaxy formation and evolution. Another challenging phenomenon is the observed behavior of satellite galaxies orbiting the Milky Way and other galaxies. These satellite galaxies tend to be arranged in vast, thin planes and move coherently, a configuration that is difficult to reconcile with the random distribution of satellite galaxies predicted by simulations based on the cold dark matter model. This puzzling arrangement, often referred to as the plane of satellite galaxies problem, suggests that there could be fundamental aspects of dark matter or the forces acting upon it that are not yet understood. Furthermore, the discovery of galaxies that appear to lack dark matter entirely, such as NGC 1052 DF2, challenges the very notion that dark matter is a necessary component of all galaxies. These anomalies invite a closer examination of the laws governing dark matter and its role in the cosmic structure. Together, these phenomena suggest that either our understanding of dark matter is incomplete or that additional physical processes are at play within galaxies. As scientists continue to investigate these galactic mysteries, they inch closer to unraveling the true nature of dark matter, potentially transforming our comprehension of the universe itself. The dark sector, comprising dark matter and dark energy, plays a pivotal role in the formation of cosmic structures, driving the evolution of the universe from its earliest moments to the intricate cosmic web observed today. At the heart of this process is dark matter, which clumps together under the influence of gravity, forming the scaffolding around which visible matter congregates. In the infant universe, slight density fluctuations, possibly imprinted by quantum fluctuations during inflation, served as seeds around which dark matter began to coalesce. These dark matter halos attracted gas and dust, leading to the formation of stars, galaxies, and eventually galaxy clusters and superclusters, woven into the vast cosmic web. Dark energy, with its repulsive force, influences the large-scale structure of the universe by driving its accelerated expansion. This expansion affects the destiny of cosmic structures, determining the rate at which galaxies move away from each other and the ultimate fate of the universe. While dark matter pulls matter together, dark energy works to tear it apart, creating a cosmic tug-of-war. The interplay between these dark components governs the pace of structure formation, with dark matter dominating in the early universe, enabling galaxies and larger structures to form before dark energy's influence becomes significant, altering the dynamics of cosmic expansion. This intricate dance between dark matter and dark energy underlies the universe's architecture, dictating the distribution and evolution of galaxies across cosmic time. Understanding the dark sector's role in cosmic structure formation is crucial for deciphering the history and future trajectory of the universe, highlighting the importance of unveiling the mysteries of dark matter and dark energy in the quest to comprehend the cosmos fully. Inside a black hole lies one of the most profound mysteries in the universe, a region where the laws of physics as we know them break down. At the heart of a black hole is the singularity, a point of infinite density where the gravitational pull is so strong that not even light can escape. This intense gravitational force results from matter being compressed into an infinitely small space at the singularity, causing the fabric of space and time to curve infinitely steeply according to general relativity. However, the true nature of what happens inside a black hole, especially at the singularity, remains speculative. Theories diverge and converge in their attempts to describe these extreme conditions. General relativity suggests that space and time as we understand them cease to exist at the singularity. Yet this classical theory of gravity doesn't mesh well with quantum mechanics, the physics of the very small leading physicists, to believe that a theory of quantum gravity, such as string theory or loop quantum gravity, might be required to fully understand the singularity. Moreover, the concept of information paradox, proposed by Stephen Hawking, adds another layer of complexity. It posits that all the information about the matter falling into a black hole appears to be lost to the universe, which contradicts the principles of quantum mechanics that information can never be lost. In essence, the insides of black holes are laboratories for the most extreme physics, where the known laws are pushed to their limits and beyond. Every hypothesis about what happens inside invites more questions, driving the continuous search for a unified theory that can reconcile the quantum world with the relativistic universe. The formation of supermassive black holes, those titanic entities that lurk at the centers of most large galaxies, including our own Milky Way, is a topic of intense research and speculation. Unlike stellar black holes, which are born from the collapse of massive stars, the origins of supermassive black holes are less straightforward and are believed to involve several possible pathways. One prevailing theory suggests that supermassive black holes might start as seeds from the collapse of massive clouds of gas in the early universe. These clouds, under the influence of their own gravity, could collapse directly to form black holes of a few hundred or even thousands of solar masses in the young universe. Over time, these initial seeds grow by accreting surrounding gas and dust and by merging with other black holes during galaxy collisions. This process of accretion and merger allows them to accumulate mass over billions of years, eventually reaching the supermassive scales observed today. Another hypothesis posits that supermassive black holes could stem from the deaths of the first generation of stars, known as population 3 stars. These stars, much larger and short-lived compared to stars that form later in the universe's history, could collapse into black holes of a few hundred solar masses. These black holes might then grow through similar processes of accretion and mergers. Additionally, there's a theory involving dense clusters of stars collapsing under their own gravity to form a single massive black hole. This process, though less commonly accepted, could also contribute to the early stages of supermassive black hole formation. Despite the differing scenarios, what is clear is that supermassive black holes are a product of the dynamic and accumulative processes in the cosmos. These processes involve the interplay of gravity, gas dynamics, stellar evolution, and galactic mergers, painting a picture of a universe where complexity builds up over cosmic timescales, eventually leading to the colossal entities that anchor galaxies today. Understanding these processes not only sheds light on the nature of supermassive black holes, but also on the formation and evolution of galaxies and the universe itself. Neutron stars, the dense remnants of collapsed massive stars, offer a unique laboratory for studying the fundamental laws of physics under extreme conditions not reproducible on Earth. These celestial objects pack about a sun's worth of mass into a city-sized sphere, resulting in densities and gravitational fields so intense that they significantly warp the fabric of space-time, as predicted by Einstein's theory of general relativity. By observing neutron stars, especially pulsars which are rapidly rotating neutron stars emitting beams of radiation, scientists can test the predictions of general relativity in the strong gravitational field regime, enhancing our understanding of gravity. Furthermore, the interior of neutron stars is thought to display matter in a superdense state known as nuclear pasta, due to its peculiar shapes reminiscent of spaghetti and lasagna. This state occurs just before matter collapses into the singularity of a black hole, offering insights into the behavior of nuclear matter under extreme densities. Such conditions allow physicists to probe the state of matter at densities beyond what can be achieved in particle accelerators, thereby testing theories of nuclear physics and the strong force that binds atomic nuclei together. Additionally, the extreme magnetic fields present in some neutron stars, known as magnetars, provide a natural laboratory for studying electromagnetism under conditions far exceeding those possible in terrestrial laboratories. The interaction between the powerful magnetic fields and the neutron star's matter can lead to spectacular phenomena, such as starquakes and giant flares, shedding light on magnetohydrodynamics and plasma physics in extreme magnetic environments. Lastly, neutron stars involved in binary systems, particularly those merging with other neutron stars or black holes, produce gravitational waves, ripples in the fabric of space-time. The detection of these gravitational waves opens a new window into understanding the universe, confirming predictions of general relativity and providing insight into the nature of matter at nuclear densities. In essence, the study of neutron stars serves as a cornerstone for exploring and unifying various domains of physics, from gravitational theories and nuclear physics to electromagnetism and quantum mechanics, furthering our quest to understand the fundamental laws that govern the universe. The information paradox is a profound quandary in theoretical physics that arises at the intersection of quantum mechanics and general relativity, specifically related to black holes. It was famously highlighted by physicist Stephen Hawking in the 1970s when he proposed that black holes emit radiation due to quantum effects near their event horizon, now known as Hawking radiation. This seemingly innocuous revelation led to a paradox. If a black hole can evaporate over time through Hawking radiation and eventually disappear, what happens to the information about the physical state of all the matter that fell into the black hole? According to the principles of quantum mechanics, information about a system's state can never be lost. It can be transformed but is always conserved. However, if the black hole vanishes, taking all its contents with it, it appears that the information about the material that formed and fell into the black hole would be irretrievably lost. This apparent loss of information contradicts quantum mechanics, presenting a puzzle that physicists have grappled with for decades. The information paradox is not just a theoretical curiosity, it touches on the very foundations of physics. It questions the nature of reality, as described by our two most successful yet mutually incompatible theories, quantum mechanics and general relativity. Resolving the paradox is vital for developing a more unified theory of quantum gravity that reconciles the quantum and classical worlds, essentially understanding the true nature of space-time and matter. Over the years, various solutions have been proposed, including the idea that information is somehow encoded in the Hawking radiation or that it escapes to a parallel universe. Another idea posits the existence of a firewall at the event horizon that would obliterate information, although this concept raises further questions. The paradox remains a focal point of research in theoretical physics, driving advancements in our understanding of black holes, quantum mechanics, and the quest for a theory of everything. Black holes, those enigmatic gravitational wells from which not even light can escape, have become unexpected crucibles for exploring the mysteries of quantum mechanics. Theoretical studies of black holes, especially the phenomenon of Hawking radiation, have revealed that these cosmic objects could hold key insights into the principles of quantum mechanics as they apply under extreme conditions. Hawking radiation, predicted by Stephen Hawking in 1974, suggests that black holes are not entirely black, but emit radiation due to quantum effects near their event horizon. This radiation implies that black holes can lose mass over time, leading to the eventual evaporation and dissolution of the black hole. This finding was groundbreaking because it represented a rare point of convergence between the realms of quantum mechanics and general relativity, two pillars of modern physics that usually operate on vastly different scales and have proven difficult to reconcile. Further exploration into the quantum aspects of black holes has led to the formulation of the holographic principle, which posits that the information content of all the matter that has fallen into a black hole might be encoded on its two-dimensional event horizon. This principle hints at a more fundamental understanding of space and time, suggesting that our three-dimensional experience might emerge from two-dimensional information patterns, challenging and expanding how quantum mechanics could be understood. Investigating black holes has also intensified the search for a theory of quantum gravity that would seamlessly combine the probabilistic nature of quantum mechanics with the geometrical fabric of space-time depicted in general relativity. In this vein, black holes serve as natural laboratories where the extremes of gravity could unlock new quantum phenomena, potentially revealing behaviors and interactions that are masked under less extreme conditions. Thus, black holes not only challenge our understanding of the cosmos, but also offer a unique pathway to probe the depths of quantum mechanics, pushing the boundaries of what is known and illuminating the path towards a more complete theory of the universe's fundamental workings. Magnetars are a rare and extreme variant of neutron stars, distinguished by their incredibly intense magnetic fields, among the strongest known in the universe, exceeding a quadrillion times that of Earth's magnetic field. These magnetic fields are so powerful that they can significantly distort the atomic structure, stretching atoms into thin, rod-like shapes. Magnetars are thought to be young neutron stars, born from the supernova explosions of massive stars, and their magnetic fields are believed to be a result of the conservation of magnetic flux and angular momentum during the collapse of the progenitor star. The significance of magnetars lies in their unique properties and behaviors, which offer insights into several areas of astrophysics and fundamental physics. For instance, magnetars are associated with some of the most energetic phenomena in the universe, including soft gamma repeaters, SGRs, and anomalous X-ray pulsars, AXPs, which are believed to be magnetars that emit intense flares of gamma rays and X-rays. These flares are so powerful that they temporarily outshine entire galaxies and can significantly affect the Earth's upper atmosphere, even from halfway across the galaxy. Studying magnetars provides a deeper understanding of the physics of neutron stars, particularly the behavior of matter under extreme magnetic fields. This in turn contributes to our knowledge of stellar evolution, the end states of massive stars, and the behavior of superdense matter. Furthermore, magnetars serve as natural laboratories to study magnetohydrodynamics and the effects of incredibly strong magnetic fields, which cannot be replicated in any earthly laboratory. The extreme conditions around magnetars also have implications for fundamental physics, including the study of quantum electrodynamics, QED, which describes how light and matter interact. The strong magnetic fields of magnetars are expected to give rise to exotic QED processes that are otherwise unobservable, offering a direct test for our understanding of the quantum vacuum and the interactions between photons and magnetic fields. Black holes offer one of the most compelling cosmic laboratories for testing the predictions of Albert Einstein's theory of general relativity, which describes gravity as the curvature of space-time caused by mass and energy. The extreme gravitational environments near black holes, where the fabric of space-time is immensely warped, provide unique conditions to observe and measure the effects predicted by general relativity in ways that are not possible with less massive and dense objects. One key way black holes are used to test general relativity is through the observation of their event horizon and the region just outside of it, known as the photon sphere. According to general relativity, light passing close to a black hole should be bent due to the curvature of space-time. This gravitational lensing effect has been observed and matches the predictions of general relativity. Another significant test involves the study of orbits around black holes. For instance, stars orbiting the supermassive black hole at the center of our Milky Way galaxy, Sagittarius A*, follow paths that can be precisely predicted by general relativity. The precession of these orbits, or their gradual shift over time, provides evidence for the theory. The detection of gravitational waves has opened a new avenue for testing general relativity. Gravitational waves are ripples in the fabric of space-time, produced by some of the most violent and energetic processes in the universe, such as the merger of black holes. The properties of these waves, including their speed, frequency, and decay over distance, align remarkably well with the predictions of general relativity, offering strong evidence in support of the theory. The recent imaging of black holes by the Event Horizon Telescope (EHT) project presents another groundbreaking test. The images of the shadow and ring of light surrounding the black hole in the galaxy M87 match the predictions of general relativity regarding the appearance of a black hole's surroundings. This visual evidence supports the theory's accuracy in describing the behavior of light and matter under extreme gravitational forces. Each of these examples highlights how black holes serve as natural proving grounds for testing the limits and validity of the theory of general relativity. By studying black holes, scientists can further explore and understand the fundamental laws that govern the cosmos, potentially paving the way for new physics that extends beyond our current theoretical framework. The field of gravitational wave astronomy has seen rapid advancement since the first detection in 2015, continually offering new insights into the cosmos. Among the latest findings, several stand out for their implications and contributions to our understanding of the universe. One significant discovery is the observation of gravitational waves from the merger of neutron stars. The event, detected in 2017, marked the first time that both gravitational waves and electromagnetic signals, gamma-ray bursts followed by visible infrared and X-ray emissions were observed from the same cosmic event. This groundbreaking observation has ushered in the era of multi-messenger astronomy, allowing scientists to combine information from different types of signals to get a more comprehensive picture of such cataclysmic events. The neutron-star merger provided insights into the origin of heavy elements like gold and platinum, suggesting that such collisions are a primary source of these elements in the universe. More recently, researchers have identified gravitational waves from what appears to be the merger of a black hole with a neutron star, an event never directly observed before. These observations offer the potential to understand the properties of matter under extreme conditions and test general relativity in new regimes. The LIGO and Virgo collaborations have also expanded our understanding of black holes, detecting mergers that produce both the smallest and largest black holes observed through gravitational waves to date. Observations include black holes that challenge prior models of stellar evolution, such as those in the mass gap between neutron stars and black holes that may be the product of previous mergers, indicating a population of black holes that have grown hierarchically through multiple merging events. The continuous improvement in the sensitivity of gravitational wave detectors is allowing for the detection of gravitational waves from more distant and varied sources, including potentially continuous gravitational waves emitted by individual rapidly rotating neutron stars. This could open up new avenues for studying the structure and behavior of these dense objects. Each new observation not only tests the predictions of general relativity, but also provides valuable data on the life cycles of stars, the formation of heavy elements, the structure of neutron stars, and the history of galaxies. Gravitational wave astronomy is rapidly becoming an indispensable tool for exploring the most violent and energetic events in the universe, continually pushing the boundaries of our knowledge. The concepts of wormholes and white holes stem from the solutions of Albert Einstein's field equations in the theory of general relativity, which described the fundamental interaction of gravitation as a result of space-time being curved by matter and energy. Both concepts, while rooted in theoretical physics, venture into the realm of cosmic speculations that push the boundaries of our understanding of the universe. Wormholes, also known as Einstein-Rosen bridges, are hypothetical tunnels in space-time that could create shortcuts for long journeys across the universe. They are predicted by the equations of general relativity, but have yet to be observed. Theoretical models of wormholes suggest that they could connect two distant points in space-time, potentially allowing for instantaneous travel between them or even time travel. However, the stability of these structures remains a significant challenge, as the laws of physics imply that wormholes, if they exist, would likely collapse too quickly for anything to pass through unless they are propped open by a form of exotic matter with negative energy density, which is itself speculative and not yet discovered. White holes, on the other hand, are considered as the theoretical opposites of black holes. While a black hole prevents anything from escaping its event horizon, a white hole is imagined to be a region in space-time that nothing can enter, only emit. They are described by the same solutions to Einstein's equations as black holes, but have never been observed. Theoretical physics suggests that white holes could be the other end of a black hole or a wormhole, ejecting matter and energy in a manner that appears to defy the laws of thermodynamics. However, the existence of white holes and their properties remain purely speculative, with no empirical evidence supporting their presence in the universe. Both wormholes and white holes captivate the imagination and play significant roles in science fiction. In scientific discourse, they serve as fascinating subjects for theoretical exploration, pushing the limits of our understanding of space-time, gravity, and the universe. These concepts challenge researchers to contemplate the full implications of Einstein's general relativity and to search for evidence of phenomena that might one day unlock new realms of cosmic exploration and understanding. The recent observations of black hole mergers have opened a window into a cosmic ballet that was previously shrouded in mystery. Among the enigmas these events present is the genesis of the gravitational waves that ripple through the fabric of space-time itself. These waves, first predicted by Albert Einstein over a century ago, were observed for the first time in 2015. But the source of these waves, particularly when it involves the merger of black holes, each several times the mass of our Sun, leaves scientists pondering the incredible forces at play. How do such massive entities come to orbit each other so closely before ultimately colliding? This question delves into the depths of galactic evolution and stellar destiny. Furthermore, these mergers challenge our understanding of the universe's expansion rate and the distribution of matter, both dark and visible. As telescopes and detection technologies improve, each black hole merger observed adds a new piece to the cosmic puzzle, offering insights but also deepening the enigma of the universe's most mysterious objects. The concept of a multiverse, where our universe is just one of potentially an infinite number of universes with their own laws of physics, has tantalized scientists for years. One piece of evidence supporting the existence of a multiverse could come from the cosmic microwave background, the afterglow radiation from the Big Bang, which permeates the universe. Scientists have observed cold spots in the CMB that are difficult to explain solely through the physics of our own universe. These anomalies could hint at gravitational forces pulling from beyond our visible cosmos, perhaps caused by other universes. Additionally, the theory of cosmic inflation, which proposes a rapid expansion of the universe just after the Big Bang, naturally leads to the formation of a multiverse. This theory suggests that different regions of space could stop inflating at different times, creating separate bubble universes. While direct evidence remains elusive, these and other scientific observations continue to fuel the debate and tantalize the imagination, suggesting that our universe might indeed be part of a grander, far more complicated multiverse tapestry. Detecting other universes, a task that teeters on the edge of science fiction, involves peering into the very limits of our understanding and technological capability. One promising approach is based on the study of the cosmic microwave background, CMB, the relic radiation from the Big Bang. Scientists are on the lookout for patterns within this radiation that could hint at interactions with other universes. Specifically, they theorize that if another universe were to collide with our own, it might leave a distinctive mark or bruise on the CMB, potentially observable with highly sensitive instruments. Another method hinges on the detection of gravitational waves, ripples in spacetime that could carry signatures from processes unexplainable by our universe alone. High-precision measurements from instruments like the Laser Interferometer Gravitational Wave Observatory, LIGO, could, in theory, uncover these signals. Furthermore, theoretical physicists propose that observing anomalies in the distribution of dark matter, which doesn't interact with light but exerts gravitational pull, might suggest influences from parallel universes. While these methods currently push the boundaries of speculation and technology, they offer intriguing pathways to potentially confirming the existence of other universes. The theoretical foundations for the concept of extra dimensions are deeply rooted in the quest to unify the fundamental forces of nature. One of the most prominent theories that proposes the existence of extra dimensions is string theory, which posits that at the most fundamental level, particles are not point-like, but rather tiny vibrating strings. These strings can vibrate at different frequencies, akin to musical notes, and these vibrations give rise to all the particles and forces in the universe. String theory suggests that for the mathematics to work out, there must be additional dimensions beyond the three spatial dimensions and one time dimension that we experience in our everyday lives. According to string theory, there could be as many as 11 dimensions, but these extra dimensions are compactified or curled up so tightly that they are imperceptible at human scales. Another theoretical foundation comes from the perspective of quantum mechanics and general relativity. Efforts to reconcile these two pillars of modern physics, one governing the very small, quantum, and the other governing the very large, cosmic, hint at the necessity of extra dimensions. In particular, theories such as supergravity and the related theory of superstrings integrate the principles of quantum mechanics with Einstein's concept of a four-dimensional spacetime, requiring additional dimensions for mathematical consistency and to possibly account for gravity's relative weakness compared to the other forces of nature. These theoretical pursuits are not just exercises in abstract mathematics, they attempt to address some of the most profound questions about the nature of reality. By proposing extra dimensions, physicists are exploring the limits of human knowledge, seeking a deeper understanding of the universe and the fundamental laws that govern it. Detecting the extra dimensions proposed by string theory poses a monumental challenge due to their incredibly small scale, generally thought to be on the order of the Planck length, which is about 100 billion times smaller than an atom. Despite this, physicists have conceived several innovative methods that might, in theory, capture evidence of these extra dimensions. One approach involves high-energy particle colliders, such as the Large Hadron Collider, LHC, where protons are smashed together at nearly the speed of light. Some theories suggest that during such high-energy collisions, some particles might momentarily disappear into extra dimensions before returning to our familiar four-dimensional space-time, possibly leaving behind subtle but detectable signals, such as an unexpected energy deficit. Another method is to look for the gravitational effects of extra dimensions on scales just above the quantum level. If gravity can leak into extra dimensions, as some theories suggest, then experiments designed to measure gravitational forces at short ranges might observe deviations from Newton's law of universal gravitation. Furthermore, astrophysical observations might offer clues. For instance, if tiny black holes were produced in the early universe, their properties and decay due to Hawking radiation could be influenced by the existence of extra dimensions, potentially leaving observable imprints in cosmic ray data or gravitational wave signals. While direct detection of extra dimensions remains elusive, these approaches exemplify the creative ways in which physicists are attempting to probe the fundamental structure of reality, pushing the limits of our understanding and technology. If the concept of a multiverse were to be proven, it would radically transform our understanding of reality, reshaping foundational concepts about the universe and our place within it. First and foremost, it would expand the scope of reality from a single, observable universe to an almost unimaginable expanse of distinct universes, each potentially governed by its own set of physical laws. This would imply that the constants and laws of physics we consider universal might only be local phenomena, applicable solely to our own universe. Furthermore, the confirmation of a multiverse would have profound implications for the nature of scientific explanation and prediction. It could offer a resolution to fine-tuning problems, where certain fundamental constants of our universe appear delicately balanced to allow for the existence of life. In a multiverse, these conditions could simply be the result of a vast cosmic lottery, with our universe being one of the lucky ones where life could emerge. On a deeper philosophical level, the existence of a multiverse could challenge our notions of determinism and causality, suggesting that multiple outcomes of any event could all be realized, but in different universes. It could also necessitate a revision of our understanding of the beginning and ultimate fate of the universe. Instead of a single, finite history, we might have to conceive of an eternal inflationary process spawning endless universes. The notion of a multiverse might also have existential implications, confronting us with the possibility that our universe, and by extension our existence, is not as unique as we might have believed. However, it might also expand our sense of wonder and curiosity, revealing an even larger, more diverse cosmic landscape than we ever imagined possible. In the context of the multiverse theory, it is not only possible but likely that the physics governing other universes could differ markedly from our own. In some multiverse models, each universe springs into existence with a unique set of physical laws and constants. The fundamental forces, gravitational, electromagnetic, strong nuclear, and weak nuclear, that shape the structure and behavior of our universe might have different strengths or properties in other universes. Likewise, the masses of elementary particles could vary, leading to radically different chemistry and potentially forms of matter that are entirely unknown to us. In universes where these constants and laws deviate significantly from our own, the implications could be profound. For instance, if the force of gravity were substantially stronger or weaker, it might affect the formation of stars and galaxies, altering the universe's capacity to host life as we know it. Similarly, variations in the electromagnetic force could impact chemical bonding, leading to forms of complexity that are unimaginable within the framework of our physics. Such diversity in the physical makeup of other universes would extend the frontiers of theoretical physics, challenging us to rethink what is fundamentally possible in a broader, more diverse cosmic context. It underscores the idea that our universe, with its specific set of laws and constants that allowed for the emergence of life, might be one of countless others, each with its own unique physical narrative. The idea of a multiverse profoundly influences philosophical and ethical considerations, extending the scope of inquiry and debate far beyond our singular universe. Philosophically, it challenges the notion of anthropocentrism, the belief that human beings hold a central and unique place in the universe, by suggesting that our universe is just one of countless others, potentially filled with diverse forms of life and intelligence. This perspective could lead to a re-evaluation of our significance and place in the broader cosmos, urging a more humble and perhaps more curious outlook on existence. From the standpoint of ethics, the multiverse introduces complexities regarding the moral value and consideration we afford to sentient beings across different universes should they exist. It raises questions about our responsibilities not just to life within our own universe, but to hypothetical beings in others, especially if our actions, for instance, experiments in physics that could have cross-universal repercussions, might impact the fabric of other universes. Moreover, the multiverse theory can influence the philosophical discussion on determinism and free will. If every possible outcome of every event transpires in some universe within the multiverse, it prompts us to reconsider concepts of choice, fate, and personal agency in a framework where every conceivable version of our lives is playing out somewhere. Finally, the multiverse concept also stirs ethical debates regarding the allocation of resources to research and science. It challenges us to think about how much effort and funding humanity should invest in exploring theories that, while potentially revealing, also stretch the limits of verifiability. This entails a philosophical balancing act between the pursuit of knowledge for its own sake and practical considerations about the benefits of such knowledge for our universe. Altogether, the multiverse theory expands the canvas of philosophical and ethical inquiry, pushing us to confront fundamental questions about reality, existence, and our place within it, all of which may never have definitive answers. Providing evidence for the multiverse presents scientists with formidable challenges, rooted in both the theoretical complexities and the practical limitations of current scientific methodologies. One of the primary hurdles is the inherent unobservability of other universes. By definition, they exist beyond the reach of our observable universe, making direct detection or interaction virtually impossible with current technology. This leads to the issue of falsifiability, a cornerstone of the scientific method. For a theory to be considered scientifically valid, there must be a conceivable way to disprove it. However, if other universes cannot be observed or measured, formulating a test that could potentially falsify the multiverse theory becomes exceedingly difficult. Another significant challenge is the reliance on indirect evidence and the interpretation of existing cosmological data, such as the cosmic microwave background or the distribution of dark matter. While anomalies or unexplained phenomena in these areas could suggest the influence of other universes, they could also be attributed to gaps in our understanding of our own universe's physics. This complexity makes it challenging to attribute such observations definitively to the effects of a multiverse. Additionally, the theoretical underpinnings of the multiverse concept arise from cutting-edge and highly speculative areas of physics, such as string theory and inflationary cosmology. These theories themselves are subject to ongoing debate and refinement within the scientific community, further complicating the quest for solid evidence of other universes. Lastly, the sheer scale and ambition of the experiments or observations necessary to provide evidence for the multiverse are daunting, requiring technologies and resources that may be beyond our current capabilities. These challenges necessitate not only advancements in physics and astronomy, but also conceptual breakthroughs in how we understand and investigate the fundamental nature of reality. Despite these obstacles, the pursuit of evidence for the multiverse continues to inspire and drive scientific exploration, pushing the boundaries of what we know about the cosmos. There are several observable effects that could indirectly hint at the existence of other dimensions, even though these dimensions themselves may be beyond direct detection due to their compact size or the nature of their interaction with our observable universe. One such effect revolves around the behavior of gravity at exceptionally small scales. Theories proposing extra dimensions suggest that gravitational force might behave differently at distances shorter than we can currently measure. Should future technologies enable us to probe gravity at the Planck scale, around 10 circumflex 35 meters, deviations from Newton's inverse square law could indicate the presence of extra dimensions. Another potential observable effect lies in the production of mini black holes in high-energy particle collisions, such as those conducted at the Large Hadron Collider, LHC. Some theories posit that the energy threshold for black hole formation could be significantly lowered in scenarios with extra spatial dimensions, leading to their possible creation and subsequent decay in particle accelerators. Observing these processes could provide indirect evidence of dimensions beyond our familiar three. Additionally, the imprint of extra dimensions could also manifest in the cosmic microwave background, the afterglow of the Big Bang. Variations in the CMB's temperature and polarization patterns that cannot be explained by standard cosmological models might indicate physics influenced by higher dimensions. Finally, the existence of particles or phenomena that cannot be explained within the standard model of particle physics might also hint at extra dimensions. For instance, the discovery of particles with unexpected masses or charges, or the observation of unexplained force carriers, could suggest interactions with fields or particles associated with higher dimensional spaces. Each of these observable effects would require precise measurements and the development of new physics theories to be understood fully, making the search for evidence of extra dimensions one of the most exciting frontiers in contemporary physics. The holographic principle proposes a fascinating and profound connection between the seemingly disparate concepts of gravity and quantum mechanics, tying into broader theories of the universe in a way that challenges our traditional notions of space and information. At its core, the principle suggests that all the information contained within a volume of space can be represented as encoded data on the boundary of that space. In a more cosmic context, this implies that our three-dimensional universe could be projected from two-dimensional information stored at its outer boundary, similar to a hologram. This principle emerges from theoretical efforts to reconcile general relativity, which describes the universe on a grand scale, with quantum mechanics, which governs the behavior of particles at the smallest scales. It was initially conceived within the context of black holes, as researchers pondered the paradox of what happens to information about the state of particles that fall into a black hole. The holographic principle helped resolve this by suggesting that such information is not lost, but encoded on the event horizon of the black hole. When applied to the universe as a whole, the holographic principle potentially offers a revolutionary framework for understanding spacetime and gravity. In this view, gravity in our universe could be a result of a holographic projection from simpler, flat universes encoded at the cosmological horizon. This leads to the intriguing possibility that what we experience as three-dimensional reality, with the force of gravity and the passage of time, might emerge from two-dimensional information processes at the universe's edge. Incorporating the holographic principle into cosmology has profound implications for fundamental physics, offering new ways to think about everything from the evolution of the universe to the quest for a theory of quantum gravity. By suggesting that space and volume might emerge from a kind of fundamental information processing, it bridges important gaps between quantum mechanics and general relativity, pushing theoretical physics into new and uncharted territories. Exotic matter refers to forms of matter that possess properties contrary to conventional matter, displaying behaviors that challenge our understanding of physics. Notably, exotic matter is often discussed in the context of negative mass or energy density, which defies the common experiences of gravity and inertia. This type of matter does not occur naturally in the observable universe under normal conditions, but is a significant concept in theoretical physics and advanced cosmology. One of the most intriguing contexts in which exotic matter is proposed is within the theorizing around wormholes and the Alcubierre warp drive, a concept for faster-than-light space travel. According to general relativity, the creation and stability of a wormhole, a hypothetical tunnel connecting distant points in spacetime, would require the existence of exotic matter. This matter would generate negative energy density, counteracting the gravitational collapse and keeping the wormhole open for passage. Similarly, the Alcubierre drive, a speculative idea based on general relativity, would utilize a bubble of exotic matter to contract space in front of it and expand space behind it, effectively allowing a spacecraft to travel faster than light by warping spacetime. In the realm of quantum field theory, the Casimir effect provides an experimentally observed phenomenon that indirectly supports the concept of exotic matter. When two uncharged parallel plates are placed very close to each other in a vacuum, they attract due to the negative pressure between them, hinting at the complex behaviors of quantum fields and the virtual particles that pop into and out of existence. Exotic matter might also exist in the core regions of neutron stars or under extreme conditions just after the Big Bang, where the conventional understanding of matter and its properties does not fully apply. However, directly observing or creating exotic matter in a controlled setting remains beyond our current technological capabilities. As such, it remains a theoretical construct, pivotal for exploring the limitations of our physical laws and the potential for technologies and phenomena that sound like science fiction today. Exotic matter, with its hypothetical properties such as negative mass or energy density, is often theorized as the key to unlocking advanced space travel technologies, like warp drives. The concept of a warp drive, popularized by science fiction but grounded in real physics, involves creating a bubble of spacetime around a spacecraft that allows it to travel faster than the speed of light relative to the space outside the bubble without violating Einstein's theory of relativity. The Alcubierre warp drive model, a notable example, suggests using a ring of exotic matter to manipulate spacetime, expanding it behind the ship and contracting it in front, to propel the vessel at unprecedented speeds. The allure of using exotic matter for such technologies stems from its potential to create the negative energy densities needed to bend or warp spacetime in this manner. In theory, if exotic matter could be harnessed or created in sufficient quantities, it might be possible to achieve faster-than-light travel, enabling humanity to explore distant stars and galaxies within a human lifetime. However, the practical challenges of realizing such technologies are immense. Currently, exotic matter is a theoretical concept, with no known methods for its creation or stabilization in the quantities that would be required for space travel applications. Moreover, generating and manipulating the vast amounts of energy needed, not to mention overcoming the technical hurdles related to the spacecraft's structure and the safety of its passengers, present significant scientific and engineering challenges. Even though the idea of utilizing exotic matter for advanced space travel technologies remains in the realm of speculation and theoretical physics, it continues to inspire research into the fundamental nature of matter, spacetime, and the possibilities for future exploration beyond our solar system. Such investigations push the boundaries of our understanding and open up new avenues for considering how humanity might one day traverse the vast expanses of space. The study of particle accelerators plays a pivotal role in advancing our understanding of the universe by probing the fundamental constituents of matter and the forces that govern their interactions. Particle accelerators, such as the Large Hadron Collider, LHC, propel subatomic particles to near-light speeds before colliding them, allowing scientists to investigate conditions similar to those a mere fraction of a second after the Big Bang. One of the most significant contributions of particle accelerator research is the experimental confirmation of the standard model of particle physics, a framework that describes 3 of the 4 known fundamental forces in the universe and classifies all known elementary particles. The discovery of the Higgs boson in 2012 at the LHC served as a keystone in this model, explaining how particles acquire mass. Moreover, particle accelerators help scientists explore beyond the standard model, searching for evidence of supersymmetry, extra dimensions, and the particles that could make up dark matter. Dark matter is an unseen substance that exerts gravitational forces on visible matter, and understanding it is crucial for unraveling the large-scale structure of the universe and its evolution. In addition to these cosmological insights, particle accelerators have also contributed to practical applications in medicine, such as cancer therapy techniques, and in industry, through the development of new materials. By pushing the frontiers of high-energy physics, particle accelerators allow us to explore the very fabric of the universe, challenging and refining our theories about the nature of reality. They are indispensable tools in the ongoing quest to understand the origins of the universe, the fundamental forces and particles that comprise it, and the underlying principles that dictate their behavior. The quest to understand the universe through physics encounters several theoretical limits that challenge our ability to fully grasp the cosmos's deepest mysteries. One fundamental limit arises from the Heisenberg uncertainty principle, a cornerstone of quantum mechanics, which posits that it is impossible to simultaneously know both the exact position and momentum of a particle. This principle underlines a fundamental limit to our knowledge of the quantum realm, suggesting that there are intrinsic limits to what we can know about the behavior of the universe at its smallest scales. Additionally, the theory of relativity introduces the concept of the observable universe, bounded by the speed of light. Regions beyond this cosmic horizon are forever inaccessible to us, as light from these parts of the universe has not had enough time to reach us since the Big Bang. This limitation means there may be vast swathes of the universe that we can never directly observe or study, potentially hiding phenomena or laws of physics not present within our observable realm. Another significant challenge is the potential existence of dark matter and dark energy, which together are thought to comprise about 95% of the total content of the universe. Despite their apparent dominance in the cosmos, these entities interact weakly, if at all, with the electromagnetic force, making them incredibly difficult to detect directly. Our understanding of the universe is fundamentally constrained until we can fully characterize these components. Moreover, as we delve deeper into theoretical physics, we encounter the limits of mathematics and computability. Certain problems may be so complex that they are computationally infeasible to solve with our current understanding and technology. Furthermore, as theories progress, they often become more abstract and detached from empirical verification, challenging the very framework of how we validate scientific knowledge. Lastly, there is the philosophical consideration that our physical theories are ultimately models created by the human mind to describe observations. There may be inherent limitations to how accurately these models can reflect reality, influenced by the biases and cognitive capacities of human understanding. While these theoretical limits present formidable challenges, they also drive the pursuit of new knowledge and technologies to push the boundaries of what is possible, leading researchers to continually refine and expand our understanding of the universe. Venturing into the realms of the unknown, scientists across the globe are on a relentless quest to unlock the mysteries of the universe, constantly pondering over the existence of particles and forces that remain elusive to our current understanding. At the heart of this inquiry lies the enigmatic concept of dark matter, a form of matter that does not emit, absorb, or reflect light, making it completely invisible and detectable only through its gravitational effects. This intriguing substance is believed to constitute about 85% of the total matter in the universe, yet it remains one of cosmology's most perplexing puzzles. Alongside dark matter, theorists have proposed the existence of dark energy, a mysterious force driving the accelerated expansion of the universe, defying the gravitational pull of galaxies. Another fascinating possibility is the existence of supersymmetric particles, hypothesized partners of the known particles that could explain several unsolved questions in particle physics. As research advances, employing formidable tools like the Large Hadron Collider and space-based observatories, we edge closer to uncovering the truths that may fundamentally alter our comprehension of the universe. These potential discoveries beckon with the promise of answering age-old questions and revealing new landscapes of knowledge that could redefine our place in the cosmos. Loop quantum gravity stands as a riveting challenger in the quest to meld the realms of quantum mechanics and general relativity, offering a fresh perspective on the fabric of the universe. At its core, this theory proposes that space itself is not a smooth, continuous expanse, as depicted in general relativity, but is composed of tiny, discrete loops, akin to the threads of a fabric. These loops are so minuscule that their size is measured on the Planck scale, which is about 100 million trillion times smaller than an atom. This groundbreaking approach suggests that space and time are granular, and their apparent fluidity emerges only at larger scales observable by humans. Should loop quantum gravity hold true, it could dramatically transform our understanding of the cosmos, especially in conditions of extreme gravity, such as those found in black holes or the universe's birth at the Big Bang. Unlike conventional theories that predict singularities, points where equations break down and physical theories cease to operate, loop quantum gravity suggests these cosmic phenomena could instead be bridges to new, vast universes or bounce points for the genesis of a new universe. This profound shift in perspective challenges the traditional view of space-time as a continuous entity and opens up exhilarating possibilities for solving some of the most profound mysteries in cosmology. Through its unique lens, loop quantum gravity holds the potential to unravel the very nature of the universe, offering a glimpse into the quantum origins of space-time itself. The Planck scale occupies an esteemed and pivotal role in theoretical physics, acting as a quantum realm gatekeeper at which the classical concepts of space and time begin to dissolve into the quantum froth of uncertainty. Defined by Planck length, Planck time, Planck mass, and other fundamental units derived from universal constants, the Planck scale represents the unimaginably tiny scales at which the effects of quantum gravity are expected to become significant. It is at this scale, roughly 10 to the minus 35 meters in size for Planck length and 10 to the minus 44 seconds for Planck time, that the smooth fabric of the universe as predicted by general relativity is theorized to break down into a quantized state. This realm is where the gravitational force is predicted to carry as much influence as the other three fundamental forces, electromagnetic, strong nuclear, and weak nuclear, which are well described by the quantum field theory. The significance of the Planck scale extends beyond mere numbers. It embodies the frontier at which the known laws of physics morph into an uncharted territory, demanding a unified theory of quantum gravity to reconcile the quantum and relativistic descriptions of the universe. Theories such as string theory and loop quantum gravity strive to illuminate this esoteric domain, suggesting a universe woven from the fine fabric of quantum loops or vibrating strands of energy. Understanding the phenomena at the Planck scale is not just a quest to peer into the quantum crevices of space-time, but a philosophical and scientific journey to decipher the cosmos's most fundamental nature. The unexplored territory of ultra-high energies, vastly beyond the reach of our current particle accelerators, tantalizes physicists with the possibility of uncovering new physical laws fundamentally distinct from those known today. At energies near the Planck scale, where the effects of quantum gravity become inescapable, the conventional framework of physics, built upon the pillars of quantum mechanics and general relativity, faces formidable challenges, suggesting that these realms might operate under principles yet to be conceived. This frontier, often associated with the very infancy of the universe moments after the Big Bang, is where the intertwined fabric of space-time could reveal exotic phenomena such as extra dimensions or the unification of all fundamental forces known as the theory of everything. Such potential discoveries promise not only to expand our understanding of the building blocks of the universe, but also to revolutionize the technological advancements they could engender. The quest to probe these energies, though daunting, inspires cutting-edge experiments and theoretical frameworks, driving the innovation of more powerful particle accelerators and sophisticated cosmological observations. The hope is that these ventures into the unknown will peel back the layers of the cosmic onion, exposing new laws of physics that govern the high-energy regime and offering profound insights into the very essence of reality itself. Entanglement and quantum mechanics stand at the vanguard of a paradigm shift, challenging the very bedrock of classical theories of the universe with phenomena that defy intuitive understanding. In the classical view, objects exist with definable properties and influences that do not surpass the speed of light, adhering to the realm of causality and determinism. However, quantum mechanics introduces the concept of entanglement, wherein particles become inexorably linked in such a way that the state of one, no matter the distance from its partner, instantaneously influences the state of the other, a phenomenon that Einstein famously derided as spooky action at a distance. This flies in the face of classical physics, which posits that no information can travel faster than the speed of light. Furthermore, quantum mechanics reveals that at the subatomic level, particles exist in states of probability rather than definitive reality, only taking on concrete properties when observed or measured. This principle shatters the classical expectation of a deterministic universe, ushering in a reality where the act of observation itself determines the state of physical systems. These quantum oddities not only question the nature of reality and the fabric of space-time, but also fuel groundbreaking technologies like quantum computing and encryption, which leverage these phenomena to perform tasks inconceivable with classical mechanics. Through its defiance of classical intuitions, Quantum mechanics thus beckons a profound reassessment of our understanding of the cosmos, promising a deeper comprehension of the universe's most enigmatic forces. The frontier of theoretical physics is dotted with profound mysteries that challenge our understanding of the universe. Among these enigmatic questions, the nature of dark matter and dark energy stands as a particularly perplexing puzzle. Despite comprising about 85% of the universe's total matter and about 70% of its total energy density, respectively, their fundamental properties and origins remain elusive, casting shadows over our comprehension of cosmic structures and the universe's accelerated expansion. Another deep mystery lies in reconciling general relativity, which beautifully describes the macroscopic world of gravity and space-time, with quantum mechanics, the framework governing the subatomic world. This quest for a theory of quantum gravity that can seamlessly merge these realms into a unified description of all physical phenomena continues to elude the finest minds, leaving questions about the true nature of space-time and the fabric of the cosmos unanswered. The puzzle of why there is more matter than antimatter in the universe challenges our understanding of fundamental symmetries and the conditions following the Big Bang. This imbalance allows the universe and life as we know it to exist, yet the mechanisms behind this disparity are not fully understood, hinting at new physics beyond our current theories. Additionally, the information paradox surrounding black holes, which pits the rules of quantum mechanics against the unforgiving grip of gravitational collapse, questions the very principles of information conservation in the universe, presenting a surreal boundary where known physics crumbles. These mysteries, among others, underscore the vastness of our ignorance and the potential for groundbreaking discoveries. They drive the quest for deeper theories, not only to illuminate the shadows of our current understanding, but to redefine the very fabric of reality as we perceive it, promising a future where the cosmos might be viewed through an entirely new lens. Fast radio bursts are intense flashes of radio waves from space, each lasting mere milliseconds, yet emitting as much energy as the sun does in several days. Their origins have puzzled astronomers since their discovery in 2007, sparking numerous theories and rigorous observational campaigns to decipher their sources. These cosmic enigmas predominantly seem to originate from galaxies billions of light-years away, far beyond our Milky Way, adding layers to their mystery and intrigue. One prevailing theory suggests that FRBs are the result of cataclysmic events, such as the collisions of dense stellar remnants like neutron stars, or the explosive deaths of highly magnetized neutron stars known as magnetars. Indeed, in 2020, astronomers traced a series of FRBs to a known magnetar within our Milky Way, providing substantial evidence that at least some of these bewildering phenomena can be attributed to magnetar outbursts. This discovery marked a significant breakthrough in our understanding, linking these mysterious signals to extreme astrophysical processes known to occur in the universe. However, the story of FRBs does not end here. The diversity in the observed properties of FRBs suggests that they might not all share the same origin. Some burst only once, leaving nothing but intrigue in their wake, while others repeat, pulsing out radio waves multiple times from the same location in the sky. This variance hints at the possibility of multiple cosmic phenomena being responsible for their production, painting a complex picture of these perplexing celestial phenomena. The cause and origins of FRBs remain a vibrant field of research, challenging our understanding of the universe and compelling us to look deeper into the cosmos, in the hope of unraveling the secrets these distant flashes of radio light hold about the extreme physics governing our universe. Cosmic rays are high-energy particles that journey through space at nearly the speed of light, striking the Earth's atmosphere with energies that dwarf those achievable by human-made accelerators. The mechanisms by which these particles attain such staggering energies have been a subject of intense investigation and debate among astrophysicists. It is believed that these cosmic messengers are accelerated by some of the most violent and energetic processes in the universe. One leading theory posits that shock waves from supernova explosions are responsible for accelerating cosmic rays to their incredible velocities. As the remnants of a supernova expand and collide with interstellar material, they create shock fronts. It is within these turbulent regions that particles may be repeatedly bounced back and forth, gaining energy with each pass through the shock front, a process akin to a cosmic pinball machine. Another potential accelerator is the supermassive black holes found at the centers of galaxies, including our own Milky Way. As matter spirals into these colossal black holes, enormous jets of plasma are ejected at high speeds into space. Particles caught in these jets can be accelerated to extremely high energies, contributing to the cosmic ray population. Magnetars, a type of neutron star with incredibly powerful magnetic fields, are also candidates for generating high-energy cosmic rays. The rapid decay of their magnetic fields releases vast amounts of energy, potentially capable of accelerating particles to the observed energies of cosmic rays. Despite these theories, the precise processes and astrophysical sites responsible for the highest energy cosmic rays still elude a definitive explanation. The mystery is compounded by the challenge of tracing cosmic rays back to their origins due to their deflection by magnetic fields that pervade space. This enigma continues to fuel research and debate, pushing the boundaries of our understanding of the universe's most extreme particle accelerators. The WOW signal, an enigmatic radio burst detected in 1977 that has since evaded a conclusive explanation, stands as a tantalizing example of the unexplained anomalies that occasionally puncture the orderly fabric of scientific understanding. Such phenomena ignite the imagination and fuel wide-ranging speculation, from the mundane to the extraordinary. The WOW signal, in particular, captured the public's attention as a potential indicator of extraterrestrial intelligence, given its seemingly artificial characteristics not readily attributable to known cosmic sources or terrestrial interference. Beyond the allure of contact with alien civilizations, the implications of unexplained anomalies like the WOW signal are profound, stirring deep philosophical and scientific contemplation. They underscore the vastness of our ignorance about the universe, highlighting gaps in our current models and theories. The pursuit of explanations for these anomalies fosters innovation in observation techniques and technologies, propelling scientific methodologies forward and often leading to serendipitous discoveries unrelated to the original phenomena under study. Furthermore, these mysteries serve as an important reminder of the necessity of skepticism and rigor in scientific inquiry. The allure of jumping to sensational conclusions underscores the importance of adhering to the principles of verifiability and repeatability. Anomalies challenge the scientific community to remain open to novel hypotheses and theories while maintaining a critical eye towards evidence and interpretation. Ultimately, the exploration of unexplained phenomena like the WOW signal enriches the scientific endeavor, fueling a sense of wonder and curiosity that drives humanity's quest for knowledge. Whether these anomalies eventually find mundane explanations or lead us to revolutionary breakthroughs, they play a crucial role in the iterative process of understanding our universe and our place within it. The study of cosmic magnetic fields opens a fascinating window into the myriad forces that shape the universe, shedding light on phenomena that span the vastness of cosmic scales, from the smallest planetary systems to the largest structures in the cosmos. These magnetic fields are not only ubiquitous, but also instrumental in dictating the dynamics of cosmic plasma, guiding the formation of stars, influencing the structure of galaxies, and affecting the propagation of high-energy cosmic rays. One of the profound revelations from studying cosmic magnetic fields is the insight they provide into the processes of galaxy formation and evolution. Magnetic fields are intertwined with the interstellar medium, playing a key role in star formation by helping to regulate the collapse of molecular clouds and the accretion of matter. Understanding these magnetic fields helps astronomers decipher the complex interplay of forces that lead to the birth of stars and influence the shape and behavior of galaxies. Additionally, cosmic magnetic fields are essential to our understanding of cosmic ray propagation. These fields scatter and redirect charged particles speeding through the galaxy, affecting their paths and the distribution of cosmic radiation. The study of how cosmic rays interact with magnetic fields enhances our comprehension of both the origin of these rays and the magnetic environments through which they travel, offering clues about the processes at work in the most extreme conditions in the universe. On even larger scales, the existence of magnetic fields in the vast voids of intergalactic space hints at mechanisms at play in the early universe, potentially related to the epoch of cosmic inflation. These intergalactic magnetic fields may carry imprints from the universe's infancy, providing astronomers with valuable artifacts that could help unravel the mysteries of the Big Bang and cosmic evolution. Through the lenses of both observation and theory, the study of cosmic magnetic fields stands as a critical endeavor in cosmology and astrophysics, promising to deepen our understanding of the universe's structure, dynamics, and history. As observational techniques and theoretical models advance, the mysteries of cosmic magnetism are poised to offer profound insights into the fabric of the cosmos. The question of whether there are unknown particles being emitted from the Sun is a fascinating one that intersects with some of the most active areas of research in astrophysics and particle physics. The Sun, a maelstrom of nuclear fusion and electromagnetic activity, is a prolific source of known particles such as neutrinos, electromagnetic radiation across the spectrum, and the solar wind, a stream of charged particles mostly consisting of electrons, protons, and alpha particles. However, the possibility of the Sun emitting previously unknown types of particles remains an open and intriguing question. One area of research that hints at this possibility is the study of solar neutrinos, elusive particles produced in vast quantities by the nuclear reactions powering the Sun. Neutrinos interact so weakly with matter that billions pass through the Earth and everything on it, every second without leaving a trace. The detection of solar neutrinos has historically challenged our understanding of particle physics, notably contributing to the discovery of neutrino oscillation, a phenomenon that implied neutrinos have mass, which was contrary to previous expectations. This revelation opened the door to new physics beyond the Standard Model, the prevailing theory of particle physics. Further theoretical propositions, such as the existence of axions or sterile neutrinos, hypothesize particles that could be produced in solar processes under certain conditions. Axions, for example, are hypothetical particles proposed as a solution to the strong CP problem in quantum chromodynamics and are also considered as a candidate for dark matter. If axions exist and are produced in the Sun, their detection could solve multiple significant puzzles in physics, from the inner workings of the Sun to the fundamental constituents of the universe. Ongoing and future experiments and observatories, such as those aiming to detect dark matter or to further study neutrinos, may uncover evidence of new particles emanating from the Sun. These discoveries could revolutionize our understanding of particle physics, astrophysics, and cosmology. Thus, while currently speculative, the prospect of unknown particles being emitted from the Sun exemplifies the potential for profound shifts in our comprehension of the universe prompted by seemingly straightforward questions. Antimatter, a counterpart to matter with opposite electrical charge, embodies one of the most enigmatic puzzles in understanding the cosmos. Its study not only challenges our grasp of fundamental physics, but also holds potential keys to unraveling some of the universe's deepest mysteries. One of the most perplexing questions regarding antimatter is the matter-antimatter asymmetry observed in the universe. According to prevailing theories of the Big Bang, matter and antimatter should have been created in equal amounts. However, what we observe is a universe overwhelmingly dominated by matter, with antimatter conspicuously scarce. This stark imbalance begs the question of what happened to the antimatter, or why there was a preferential production or survival of matter over antimatter in the early universe. Solving this asymmetry could provide critical insights into the conditions and laws governing the universe shortly after its inception. Furthermore, antimatter serves as a unique probe into the fundamental symmetries of physics. Studies involving antiparticles allow physicists to test the principles of charge parity time symmetry, which posits that the laws of physics should remain unchanged if charge, parity, and time are simultaneously reversed. Any observed violation of CPT symmetry in antimatter experiments could signal new physics beyond the Standard Model, challenging our current understanding of the universe's fundamental forces and constituents. Additionally, the behavior of antimatter in gravitational fields remains largely untested. Theoretically, antimatter should be affected by gravity in the same way as matter. However, experimental verification of this principle is challenging due to antimatter's propensity to annihilate upon contact with matter, making it difficult to observe over periods or in conditions where gravitational effects can be accurately measured. Confirming or refuting this aspect of antimatter could have implications for gravitational theory, dark matter, and models of the universe's overall structure. The irregular distribution of galaxies in the universe, with its vast voids and filamentous structures, poses an intriguing puzzle that has captivated astronomers and cosmologists. This cosmic web, characterized by dense clusters of galaxies separated by nearly empty voids, underscores the complexity of the universe's large-scale structure. To explain this uneven architecture, scientists turn to the theories of dark matter and the inflationary model of the universe. Dark matter, an invisible substance that does not interact with electromagnetic forces and thus cannot be directly observed, is believed to constitute about 85% of the total matter in the universe. Its presence is inferred from gravitational effects on visible matter and the cosmic microwave background radiation. The leading theory posits that shortly after the Big Bang, the universe experienced slight quantum fluctuations. These fluctuations, magnified by the rapid expansion of the universe during cosmic inflation, became the seeds for the distribution of dark matter. Over billions of years, dark matter clumped together under the force of gravity, forming an intricate scaffold on which ordinary visible matter could accumulate. This process of structure formation is thought to underlie the cosmic web's genesis. Galaxies formed and gathered in regions with higher concentrations of dark matter, creating the filamentous structures and galaxy clusters we observe today. Concurrently, regions with less dark matter ended up as voids, vast empty spaces with few or no galaxies. The gravitational interaction of dark matter with baryonic, ordinary matter, thus played a crucial role in shaping the universe's large-scale structure. Moreover, the cosmic microwave background radiation, relic radiation from the Big Bang, provides a snapshot of the early universe that supports this theory. Minute temperature variations in this radiation offer clues to the initial density fluctuations that, under the influence of gravity, led to the uneven distribution of galaxies. Through observations and simulations, scientists continue to refine their understanding of dark matter's role and the dynamics of cosmic inflation in forming the universe's structure. These efforts not only illuminate the processes that sculpted the cosmos's vast expanses, but also underscore the interplay between the seen and unseen components of the universe, weaving a more comprehensive picture of its grand design. The Great Attractor and the Great Wall are two remarkable phenomena that underscore the awe-inspiring scale and complexity of the universe, revealing the presence of colossal structures that dominate the cosmic landscape. The Great Attractor is a gravitational anomaly located roughly 220 million light-years away in the direction of the constellations Hydra and Centaurus. This region exhibits a gravitational pull that affects not only our own Milky Way galaxy, but also hundreds of other galaxies within a radius of millions of light-years. Despite being partially obscured by the Milky Way, making direct observations challenging, the Great Attractor is thought to be a massive concentration of galaxies, hot gas, and dark matter. Its significance lies in its immense gravitational influence, which provides critical evidence for the existence of superstructures in the universe that play a dominant role in the motion of galaxies, shaping the large-scale structure of the cosmos. The Great Wall, more formally known as the Sloan Great Wall, is another monumental structure, discovered to be one of the largest known superstructures in the universe. It is a vast filament of galaxies stretching over 1 billion light-years, located approximately 1 billion light-years from Earth. The Great Wall's discovery provided startling insight into the scale of cosmic structures, demonstrating that the universe is not homogeneous on large scales, but instead is woven into an intricate tapestry of galaxy clusters, filaments, and voids. The existence of such large-scale structures challenges our understanding of the cosmos, prompting further exploration into the forces and processes that have shaped the universe over billions of years. Both the Great Attractor and the Great Wall highlight the significance of gravity in organizing matter into the cosmic web, influencing the distribution and movement of galaxies across vast distances. These phenomena invite a deeper investigation into the nature of dark matter and dark energy, which are thought to play crucial roles in the formation and evolution of such superstructures. By studying these and other colossal formations, astronomers and cosmologists hope to unravel the mysteries of cosmic evolution, shedding light on the underlying principles that govern the structure and dynamics of the universe. Anomalies in cosmic radiation patterns hold the tantalizing potential to suggest new physics beyond our current understanding, serving as gateways to unraveling the deeper intricacies of the universe. Cosmic radiation, encompassing phenomena such as the cosmic microwave background radiation and high-energy cosmic rays, provides a fundamental observational foundation for cosmology and particle physics. However, anomalies or unexpected patterns within this cosmic backdrop can challenge existing paradigms and fuel the search for new theoretical frameworks. For instance, certain anomalies in the CMB, such as the cold spot or unexplained asymmetries and alignments in temperature fluctuations, have spurred debates and speculative theories that range from the existence of vast cosmic voids to the influence of other universes within a multiverse framework. Similarly, discrepancies in the behavior or origin of high-energy cosmic rays could indicate new physics. These particles reach energies unattainable by human-made accelerators, and their precise sources remain elusive. Anomalous patterns in their distribution, origin, or interaction with cosmic backgrounds could provide clues about the nature of dark matter, hint at previously unknown fundamental particles, or reveal novel astrophysical phenomena. The pursuit of explanations for these anomalies often leads to the development of innovative theoretical models or the proposal of new constituents of the universe. This can include extensions to the standard model of particle physics, novel mechanisms of particle acceleration, or hypotheses about the fabric of spacetime itself. Moreover, these anomalies drive the advancement of observational technologies as scientists endeavor to gather more precise data to either confirm or refute the presence of new physics. In the shadowy expanse of space, telescopes have become our eyes, reaching into corners of the universe that were once beyond our grasp. Among their discoveries are signals so mysterious they have stirred the scientific community into a whirlwind of speculation and research. Known as fast radio bursts or FRBs, these are intense flashes of radio waves lasting mere milliseconds, yet they release as much energy as the sun does in days. Detected for the first time in 2007, the origins of these enigmatic bursts remain a tantalizing puzzle. While theories abound, ranging from starquakes to highly magnetized neutron stars, and even the controversial notion of alien spacecraft, no definitive explanation exists. These fleeting, powerful signals are a humble reminder of how much remains unknown, inviting scientists and the public alike into the cosmic detective story that challenges our current understanding of the universe. The cosmos is an expanse beyond comprehension, with its hundreds of billions of galaxies, each teeming with countless stars and even more planets. In this vastness, the likelihood of life existing elsewhere in the universe shifts from the realm of science fiction closer to that of feasibility. The discovery of extraterrestrial life, even in its simplest microbial form, would mark a paradigm shift in human thought and society unparalleled by any previous scientific discovery. At its core, it would challenge our understanding of life itself, potentially rewriting biology textbooks and offering new insights into the origins of life on Earth. The realization that we are not alone in the universe could bring about profound philosophical and theological introspection, questioning long-held beliefs about humanity's place in the cosmos. Additionally, such a discovery could foster a renewed sense of unity among people, highlighting our shared identity as Earth's inhabitants in the vast expanse of space. On a more practical level, it could accelerate space exploration efforts, driving technological advancements and possibly international collaborations to study and perhaps even communicate with extraterrestrial life. Despite the potential for disruption, this monumental discovery would open up new horizons for understanding, cooperation, and exploration, marking a new chapter in human history. Biosignatures, the subtle fingerprints of life, hold the key to unlocking the mysteries of life's existence beyond our planet. These indicators of biological processes can range from specific molecules like oxygen and methane to more complex organic compounds, all of which might suggest the presence of life. By analyzing the atmospheric composition of exoplanets using spectroscopy, a technique that unfolds the spectrum of light to identify chemicals, we can search for these telltale signs across the vast distances of space. When a planet passes in front of its star, the star's light filters through the planet's atmosphere. If present, biosignatures absorb specific wavelengths of this light, creating detectable patterns that space telescopes can record. This method, albeit challenging due to the faint signals and the vast distances involved, offers a promising window into identifying environments that might harbor life. The launch of more advanced space telescopes equipped with the capability to carry out such detailed spectroscopic analysis brings us closer to the tantalizing prospect of finally answering whether we are alone in the universe. Through the meticulous study of these biosignatures, scientists worldwide hold a cautious yet hopeful outlook on uncovering the cosmic story of life. The conditions for a planet to support life as we understand it hinge on a delicate balance of factors, often described as lying within the Goldilocks zone, neither too hot nor too cold, but just right for liquid water to exist. This zone varies around stars based on their size and heat output, but the presence of liquid water is crucial because it is a universal solvent and medium where biochemical reactions vital for life can occur. Besides water, a life-supporting planet needs a stable atmosphere to protect organisms from harmful space radiation and to help moderate the planet's climate. The atmosphere's composition is equally important, with elements like carbon, hydrogen, oxygen, nitrogen, sulfur, and phosphorus considered essential for life as we know it. Another often overlooked condition is geological activity. Volcanic activities, for instance, can recycle vital minerals and gases, helping to maintain the planet's habitability over time. While these are the conditions that life on Earth depends on, the search for extraterrestrial life also remains open to the possibility that life elsewhere might not follow the same rulebook, expanding the definition of habitability beyond our Earth-centric view. The hunt for extraterrestrial life often carries an Earth-centric perspective, assuming that life elsewhere must mirror the carbon-based, water-dependent forms we know. However, the vastness of the universe and the diversity of conditions on other planets and moons inspire a broader speculation about life rooted in different chemistries. Silicon, for instance, shares many chemical properties with carbon, leading scientists to theorize about silicon-based life forms that could exist in environments lethal to carbon-based organisms. Similarly, while water is the life-sustaining solvent on Earth, other liquids, such as liquid methane or ammonia, under different temperature and pressure conditions, could potentially serve as solvents for life on planets or moons with much colder climates than Earth. These theoretical life forms would have to evolve mechanisms radically different from terrestrial life to harness energy, grow and reproduce, challenging our fundamental understanding of biology. While these concepts remain speculative, they broaden the scope of astrobiology and encourage a more inclusive search for life in the universe, reminding us that life, if it exists elsewhere, might be stranger than our earthbound imaginations have yet conceived. Defining life, especially from a cosmic perspective, plunges scientists into a complex web of philosophical, biological, and astrobiological challenges. On Earth, life is broadly characterized by traits such as metabolism, growth, response to stimuli, and reproduction. However, these criteria are deeply rooted in the carbon-based, water-reliant forms of life with which we are familiar. The vastness and diversity of the universe suggest that life outside our planet might not adhere to the same set of rules. For instance, could a silicon-based entity in an environment of liquid methane on a distant moon, exhibiting patterns of organization and energy utilization unlike anything seen on Earth, be considered alive? The problem extends into the detection of extraterrestrial life. Our tools and instruments are calibrated to search for biosignatures that mirror those of Earth, potentially overlooking entirely different manifestations of life. Moreover, the boundary between complex, self-organizing systems that might be considered alive and simpler, non-living structures becomes blurred when we step into the unknown realms of the cosmos. Addressing these challenges requires an interdisciplinary approach, melding insights from biology, chemistry, astronomy, and philosophy to conceive a more universal definition of life. This pursuit not only expands our understanding of life's potential forms and habitats, but also deepens our appreciation of the fundamental processes that animate the natural world. Engaging with these profound questions encourages humanity to look beyond our terrestrial biases, contemplating the myriad ways the cosmos might harbor the marvelous phenomenon we call life. Extremophiles, The hardy organisms that thrive in conditions once thought uninhabitable to life are key players in expanding our understanding of life's potential beyond Earth. These organisms inhabit environments ranging from the scorching heat of hydrothermal vents on the ocean floor, acidic hot springs, the crushing pressure of deep sea trenches, to the frozen deserts of Antarctica. Their existence reveals life's remarkable adaptability and hints at the diverse conditions under which life might survive elsewhere in the universe. Studying extremophiles, scientists uncover the biochemical and genetic adaptations that enable these organisms to thrive in extreme conditions. This knowledge broadens the criteria used in the search for extraterrestrial life, suggesting that planets and moons previously deemed uninhabitable might in fact be conducive to life, albeit life as we might not previously have conceived it. For instance, the discovery of microbes that can utilize sulfuric compounds for energy instead of sunlight on Earth supports the possibility of life forms in the subsurface oceans of icy moons like Europa, where sunlight doesn't penetrate. Moreover, extremophiles help in refining our search for biosignatures, the chemical indicators of life, by demonstrating that life can not only survive, but also flourish in environments with vastly different chemistries than the surface of Earth. As we send probes to Mars, Titan, and beyond, equipped with instruments designed to detect life, the study of extremophiles ensures that our search is attuned to the broadest possible spectrum of life, as diverse and tenacious as found on our own planet. The harsh environments of Venus and the gas giants in our solar system pose significant challenges to the existence of life as we know it. Venus, with its thick, toxic atmosphere composed mostly of carbon dioxide, surface temperatures hot enough to melt lead, and crushing atmospheric pressure, seems an unlikely host for life. However, recent studies have suggested that microbial life could potentially exist in the more temperate, acidic cloud decks of Venus, where temperatures and pressures are more Earth-like. The discovery of phosphine gas in Venus's atmosphere has spurred scientific debate, as on Earth, phosphine is associated with biological processes, suggesting the tantalizing possibility of aerial microbial life. The gas giants, Jupiter, Saturn, Uranus, and Neptune, present a different set of challenges. Their lack of a solid surface and extreme pressure and temperature conditions deeper into their atmospheres make the existence of life as we know it highly unlikely. However, the interest in these planets from an astrobiological perspective lies more with their moons. Several of these moons, such as Jupiter's Europa and Saturn's Enceladus, harbor subsurface oceans beneath their icy crusts. These environments, protected from the harshness of space, could potentially support life, drawing analogies to Earth's extremophiles living in extreme conditions. The concept of life in these environments would likely be vastly different from terrestrial life, perhaps relying on chemosynthesis as opposed to photosynthesis for energy. While the direct evidence for life in these environments remains elusive, the potential for life in such hostile conditions expands our understanding of the resilience and diversity of life forms, prompting us to look for life in places we once deemed impossible. The discovery of microbial life on Mars would stand as a monumental milestone in our quest to understand the universe and our place within it. It would immediately affirm the existence of life beyond Earth, dispelling the notion of our planet as a unique cradle of biology. Such a discovery would have profound implications across multiple domains. Scientifically, it would launch a new era of astrobiology, dedicated to understanding how life emerged independently on Mars and Earth, and possibly elsewhere. Researchers would delve into analyzing the Martian microbes' biology, comparing their genetic, biochemical, and physiological features to Earth's life forms. This could illuminate new aspects of biochemistry that are universal, as well as those that are planet-specific, offering fresh insights into life's adaptability and resilience. The discovery could have practical implications for future Mars exploration and colonization plans. Knowing that life exists on Mars would necessitate strict planetary protection measures to prevent cross-contamination, protecting both Earth's and Mars biospheres. Overall, finding microbial life on Mars would not only answer one of humanity's oldest questions, are we alone, but also pose new ones about the nature of life itself, propelling humanity into a new frontier of exploration and discovery. The Fermi paradox, named after physicist Enrico Fermi, highlights the contradiction between the high probability of extraterrestrial civilizations in the universe and the complete lack of evidence for or contact with such civilizations. Interpreting the silence of the Fermi paradox stirs a fascinating debate across scientific, philosophical, and speculative realms. One interpretation is the rare Earth hypothesis, which posits that while basic life forms might be common, the complex chain of circumstances that led to intelligent life on Earth is incredibly rare. According to this view, the precise conditions and evolutionary paths that foster intelligent, technologically advanced life are so improbable that we might indeed be alone in our galaxy, or even the observable universe, as its only current sapient observers. Another perspective considers the limitations of our detection methods and the vastness of space-time. The silence might simply be due to the fact that other civilizations are too far away, their signals haven't reached us, or we're not listening at the right time or in the right way. Additionally, advanced civilizations might communicate through means beyond our current technological understanding, or have deliberately isolated themselves from lower-tech societies like ours. A more theoretical interpretation invokes the Great Filter theory, suggesting that all or most life in the universe inevitably faces one or multiple insurmountable barriers that prevent it from progressing to an advanced, spacefaring stage. Whether this barrier lies in the past, such as the emergence of life itself, or the leap from prokaryotic to eukaryotic cells, or still lies ahead of humanity, remains a subject of intense speculation and concern. Each of these interpretations, among others, reflects the profound implications of the Fermi paradox. It not only underscores our current limitations in searching for extraterrestrial life, but also provokes deeper questions about our understanding of life, evolution, and our place in the cosmos. The silence, thus far, serves as a humbling reminder of the mysteries that yet elude us and the speculative nature of our quest to find others like ourselves in the vastness of the universe. The next generation of telescopes, both ground-based and spaceborne, promises to revolutionize our understanding of the universe, pushing the boundaries of our cosmic exploration further than ever before. Among these marvels of engineering and science are the James Webb Space Telescope, the Extremely Large Telescope, the 30-meter telescope, and the Giant Magellan Telescope. The James Webb Space Telescope, launched in December 2021, is designed to observe the universe in infrared, allowing it to peer through cosmic dust clouds and gaze further back in time than any telescope before it. It aims to study the formation of the earliest galaxies, stars, and planetary systems, shedding light on the universe's infancy and the origins of key cosmic structures. On the ground, the Extremely Large Telescope, under construction in the Atacama Desert of Chile, will boast a primary mirror 39 meters in diameter, making it the world's largest optical/near-infrared telescope once completed. Its immense size will grant astronomers unprecedented clarity and sensitivity, enabling the direct imaging of exoplanets, the detailed study of the universe's accelerating expansion, and insights into dark matter and dark energy. Similarly, the 30-meter telescope and the Giant Magellan Telescope will push the limits of our astronomical capabilities. The TMT, planned for construction at Mauna Kea, Hawaii, will explore the formation of early galaxies and black holes, while the GMT, being built in Chile, will excel in the discovery and characterization of exoplanets, including the analysis of their atmospheres for potential biomarkers. Together, these next-generation telescopes will offer a deeper, more detailed view of the cosmos, potentially discovering new physical phenomena and further unraveling the mysteries of dark matter, dark energy, the formation of cosmic structures, and perhaps most tantalizing, the conditions for life throughout the universe. Their observations promise to redefine our cosmic narratives and potentially place humanity in a broader cosmic context. Artificial intelligence and machine learning are poised to revolutionize our understanding of cosmic data, ushering in a new era of astronomical research. The vast quantity of data generated by astronomical observations has long surpassed the capacity for manual analysis. AI and machine learning offer powerful tools to sift through this data deluge, identifying patterns and anomalies that human researchers might overlook. These technologies can automate the process of classifying galaxies and detecting transient cosmic events, such as supernovae or fast radio bursts, with unprecedented speed and accuracy. By training machine learning algorithms on large datasets, researchers can refine their models to recognize specific objects or phenomena, dramatically reducing the time required for discovery and allowing for real-time data analysis. Moreover, AI can simulate complex cosmic processes, providing insights into the dynamics of galaxy formation, star development, and planetary system evolution. These simulations can help astronomers test hypotheses and explore scenarios that are impossible to observe directly, pushing the boundaries of theoretical astrophysics. Perhaps most exciting is the potential for AI to reveal unexpected insights from existing data, unlocking new scientific questions and challenging our current understanding of the cosmos. For instance, machine learning algorithms might identify previously unrecognized patterns in the distribution of galaxies or uncover subtle signals of exoplanets in the archival data of space telescopes. As AI and machine learning technologies advance, their integration into astronomical research will undoubtedly accelerate the pace of discovery, transforming our understanding of the universe and potentially uncovering answers to some of the most profound questions about the cosmos. Current space exploration technologies, despite their remarkable achievements, face a myriad of limitations that constrain our quest to understand the universe and our place within it. One of the primary hindrances is the vast distances involved. Even the closest stars to our solar system are over 4 light-years away, making interstellar travel with present technology a near impossibility due to the enormous timescales and energy requirements. The speed at which we can propel spacecraft is minuscule compared to the vast distances of space, confining most exploration to our solar system. Another significant limitation is the reliance on chemical propulsion systems, which, despite advances, offer relatively low efficiency for the energy they consume. This not only limits the speed and range of spacecraft, but also the payload they can carry, as a significant portion of the launch weight is dedicated to fuel. The hostile environment of space presents additional challenges, including radiation, microgravity, and extreme temperature variations, all of which can adversely affect spacecraft systems and human health. These factors complicate manned missions beyond the Moon or Mars, requiring extensive shielding and life support systems that increase mission costs and complexity. Communication delays are another constraint, especially for missions to the outer planets and beyond, where it can take hours for signals to travel between Earth and the spacecraft, hindering real-time operation and potentially delaying responses to critical situations. Finally, the economic cost of space exploration remains high, despite reductions in launch costs. The development, launch, and operation of space missions require substantial investment, often with uncertain returns, making funding and resource allocation a continual challenge. Addressing these limitations will require innovative approaches, such as advanced propulsion technologies, autonomous systems for spacecraft operation, and international cooperation to share the financial and technological burdens of space exploration. As we push the boundaries of existing technologies, the hope is to overcome these hurdles, opening up new horizons in our quest to explore the cosmos. Future missions to asteroids and comets hold the potential to unravel the mysteries of our solar system's origins and early history. These celestial bodies are considered the building blocks of the solar system, relatively unchanged remnants from its formation over 4.6 billion years ago. As such, they carry pristine materials from that era, offering a unique window into the past. Asteroids, primarily located in the asteroid belt between Mars and Jupiter, are composed of rock and metal and are thought to be remnants of the early solar system that never coalesced into a planet due to Jupiter's massive gravitational influence. Investigating their composition can reveal insights into the processes that governed the formation of terrestrial planets and the distribution of materials in the early solar system. Comets, composed of ice, dust, and organic compounds, originate from the colder outer regions of the solar system. Their nuclei contain volatile compounds that have been preserved in the deep freeze of space, acting as time capsules. Studying comets can provide valuable information about the solar system's outer reaches and the role these bodies played in delivering water and organic compounds to Earth, potentially contributing to the emergence of life. Future missions equipped with advanced instruments aim to collect and return samples from these celestial bodies to Earth for detailed analysis. Such missions could identify the exact composition of these objects, including isotopic ratios and the presence of complex organic molecules, offering clues about the conditions and processes at play in the early solar system. In addition, by closely observing the physical and chemical processes that occur on asteroids and comets, such as outgassing behaviors, interactions with the solar wind, and the effects of collisions, scientists can gain insights into the broader dynamics of our solar system's development. Exploring the vast uncharted territories of space requires groundbreaking innovations in technology, particularly in propulsion, life support systems, and space habitat designs. Beyond the Moon and our neighboring planet, Mars lies the broader solar system, where distances stretch into millions and even billions of miles. For humans to explore these faraway destinations, advancements in propulsion technology are paramount. Traditional chemical rockets, while effective for short-distance travel, are insufficient for the long hauls involved in deep space exploration. Thus, scientists are delving into alternative propulsion methods, such as ion thrusters and nuclear thermal propulsion, which promise to dramatically reduce travel time to distant planets and beyond. Another critical innovation lies in the development of sustainable life support systems that can provide astronauts with the necessary air, water, and food for years, not just days or months. These systems must be highly efficient, recycling as much as possible to limit the need for resupply missions. Lastly, creating space habitats that can shield explorers from the harsh realities of space, including cosmic radiation and extreme temperatures, while providing a semblance of Earth-like living conditions, is essential. Innovations in materials science and modular design are making these space habitats more feasible, though much work remains. Together, these advancements will pave the way for humanity's next giant leap into the cosmos, unlocking mysteries far beyond our current reach. The advancement of space travel technology plays a crucial role in enhancing our search for extraterrestrial life, fundamentally transforming our approach and expanding the scope of our exploratory missions. With each technological breakthrough, we're able to probe deeper into space, reaching previously inaccessible regions. For instance, the development of more powerful telescopes and remote sensing instruments allows us to detect exoplanets orbiting distant stars, analyze their atmospheres for signs of life, and identify planets that lie within habitable zones, where conditions may be ripe for life as we know it. Moreover, sophisticated rovers and landers equipped with state-of-the-art laboratories are being deployed to explore the surfaces of planets and moons within our solar system, searching for biosignatures or markers of past or present life. These missions to Mars, Europa, and Titan, to name a few, have been made possible by advances in robotics, artificial intelligence, and propulsion technology. Each new piece of data collected adds to our understanding of the conditions necessary for life and the potential for its existence beyond Earth. Furthermore, the pursuit of innovative propulsion methods, such as ion drives or solar sails, promises to speed up space travel significantly, potentially allowing us to send probes to the far reaches of our galaxy and beyond. As technology propels us forward, the dream of discovering life beyond our planet becomes increasingly within reach, expanding our knowledge and challenging our understanding of life in the universe. The elusive nature of dark matter and dark energy, two components believed to make up a staggering majority of the universe's mass energy content, has puzzled scientists for decades. Yet, with the horizon of technology ever expanding, new methods are emerging to potentially unveil the mysteries surrounding these unseen forces. One promising avenue is the development of highly sensitive detectors designed to directly observe particles that dark matter might be composed of, such as weakly interacting massive particles, WIMPs. Facilities like the Large Underground Xenon experiment have pushed the boundaries in this direct detection approach, using liquid xenon to attempt to capture interactions between dark matter particles and ordinary matter. On the front of dark energy, which is theorized to be driving the accelerated expansion of the universe, advanced telescopes and observatories are being equipped with sophisticated instruments to map the cosmos in unprecedented detail. Projects such as the Dark Energy Spectroscopic Instrument, DESI, aim to create a 3D map of the universe, observing millions of galaxies. By examining how the distribution of galaxies has evolved over time, scientists can infer the properties of dark energy, and how it influences the fabric of space itself. Furthermore, another innovative approach involves the use of gravitational wave detectors. These instruments, such as LIGO and Virgo, which have already proven successful in detecting ripples in space-time produced by colliding black holes and neutron stars, may also have the potential to offer insights into dark matter and dark energy by observing how these invisible entities affect the propagation of gravitational waves. While the direct detection of dark matter and the precise characterization of dark energy remain formidable challenges, these technologies represent beacon lights on the path to what could be some of the most profound discoveries in physics, potentially reshaping our understanding of the very structure and fate of the universe. Quantum computing, with its revolutionary approach to processing information, holds immense potential to transform our ability to simulate and understand the intricacies of the universe. Unlike classical computers, which process bits of information as either 0s or 1s, quantum computers utilize quantum bits or qubits, which can represent and process a vast amount of information simultaneously due to the principles of superposition and entanglement. This leap in computational capacity could dramatically enhance our ability to model complex systems that are currently beyond the reach of classical computing. In cosmology and astrophysics, for example, quantum computing could enable the simulation of the universe at an unprecedented scale and detail, from the behavior of galaxies to the interactions between fundamental particles. It could offer insights into the mysteries of dark matter and dark energy by allowing for simulations that accurately represent their effects on the cosmos. Moreover, in the realm of particle physics, quantum computing may facilitate the exploration of the quantum vacuum and the fundamental forces of nature, potentially unveiling new particles and interactions. Additionally, quantum computing could significantly advance our understanding of quantum mechanics itself, allowing for simulations of quantum systems that are inherently difficult for classical computers to handle. This includes complex quantum phenomena such as superposition, entanglement, and quantum tunneling, which are pivotal for unlocking deeper truths about the fabric of reality. By providing the tools to tackle these computational challenges, quantum computing not only promises to extend our scientific knowledge, but also to solve some of the most profound and perplexing questions about the universe and our place within it. As technology marches forward, the synergy between quantum computing and the physical sciences stands as a testament to humanity's enduring quest for understanding. The deployment of powerful artificial intelligence, AI, in space exploration brings forth a host of ethical considerations that must be carefully navigated. One primary concern is the autonomy of AI systems. As we entrust AI with more critical tasks, from piloting spacecraft to making decisions during exploratory missions on distant planets, the question arises, to what extent should AI operate independently? Ensuring that these systems can make safe, ethical decisions without human oversight, especially in unforeseen situations, is paramount. Another ethical consideration is the preservation of extraterrestrial environments. As AI technologies enable us to reach and potentially interact with previously untouched worlds, we must consider our impact on these celestial bodies. The principle of planetary protection aims to prevent biological contamination, safeguarding not only the scientific integrity of our explorations, but also any potential ecosystems that might exist. The directive to do no harm extends beyond Earth, urging us to use AI responsibly to preserve the pristine nature of these environments for future research and the potential for life. Data privacy and security represent additional ethical challenges. Space exploration generates vast amounts of sensitive data, from the mapping of distant planets to the detailing of potential resources. Ensuring the privacy and security of this data against misuse, especially when AI is involved in processing and analyzing this information, is critical. Furthermore, the equitable sharing of knowledge and resources discovered through AI-assisted space exploration raises questions about accessibility and the democratization of space science. Lastly, the ethical development and deployment of AI in space exploration call for transparency, accountability, and inclusivity. This includes collaborating across nations and cultures, involving a diverse set of stakeholders in decision-making processes, and ensuring that the benefits of space exploration, enhanced by AI, are shared widely and equitably. As we stand on the precipice of a new era in space exploration, propelled by advancements in AI, it's essential that ethical considerations guide our journey, ensuring that we explore responsibly and conscientiously, with respect for the unknown and the integrity of the cosmos at the forefront of our endeavors. International collaborations play a pivotal role in enhancing our capabilities to study the universe, leveraging the collective resources, expertise, and perspectives of the global scientific community. Such partnerships allow for the pooling of financial and technological resources, which is crucial for launching ambitious projects that would be beyond the reach of any single nation. For instance, the construction and operation of large-scale facilities such as the Atacama Large Millimeter Submillimeter Array, ALMA, in Chile, or the upcoming Square Kilometre Array, SKA, set to be built in Australia and South Africa, are made possible through international consortia. These powerful observatories provide unparalleled insights into the cosmos, from the formation of stars and planets to the detection of complex molecules that could hint at life's building blocks. In addition to resource sharing, international collaborations foster a diverse scientific community, bringing together a wide range of expertise and research traditions. This diversity is invaluable in developing innovative approaches to research and problem-solving, leading to breakthroughs that might not occur within more homogeneous or isolated research environments. It also offers opportunities for cross-training and education, preparing a new generation of scientists with a broad global perspective on cosmic exploration. Moreover, international partnerships in space exploration embody a shared spirit of curiosity and discovery that transcends geopolitical boundaries. They can act as bridges between nations, fostering peaceful cooperation and mutual understanding amidst a quest that unites humanity, comprehending our place in the universe. By working together, countries can also address common challenges such as space debris management and the responsible use of space, setting standards and protocols that ensure a sustainable future for space exploration. Ultimately, international collaborations in the study of the universe not only maximize our scientific return, but also remind us of our shared humanity, highlighting how much more can be achieved when we unite in the pursuit of knowledge beyond our world. The discovery of evidence pointing to past universes would represent a monumental shift in our understanding of cosmology and the very nature of reality itself. This would imply that our universe is not the singular, isolated event we once thought it to be, but rather a link in an immeasurably vast chain of cosmic existence. Such a finding would lend weight to theories like the cyclic universe model, which posits that the universe undergoes an infinite series of expansions and contractions, or the multiverse theory, suggesting the existence of multiple or even an infinite number of universes. From a scientific perspective, this discovery would propel an unprecedented revolution in physics, prompting a re-evaluation of the fundamental laws that govern the cosmos. The insights gained could potentially resolve long-standing puzzles such as the nature of dark matter and dark energy, the reasons for the apparent fine-tuning of the universe for life, and the initial conditions that led to the Big Bang. Theoretical frameworks that until now have been purely speculative could find concrete support, pushing the boundaries of science into new, uncharted territories. On a philosophical and existential level, evidence of past universes would profoundly alter our perspective on our place within the cosmos. The realization that our universe is but one of many could have a humbling effect, expanding our cosmic perspective and challenging deeply held beliefs about the universe's origin and ultimate fate. Moreover, it could open up new contemplations on the nature of time, causality, and the possibility of life and civilization in these other universes. In practical terms, such a discovery would likely galvanize public and scientific interest in further explorations of the cosmos, potentially leading to increased funding and international cooperation aimed at unlocking the mysteries of the universe. It would underscore the importance of space exploration and astrophysical research, not just for gaining knowledge about our own universe, but for understanding the broader cosmic landscape in which it resides. Ultimately, finding evidence of past universes would be one of the most profound discoveries in human history, expanding our knowledge of the cosmos in ways we can hardly imagine and forever changing our understanding of reality. The concept of time, one of the most enigmatic and fundamental aspects of the universe, undergoes fascinating variations across different cosmological models, reflecting the diverse ways in which scientists and philosophers understand and interpret the cosmos. In the standard Big Bang model, time is considered to begin at a singular point approximately 13.8 billion years ago, initiating the expansion of the universe from an infinitely dense state. Here, time is linear, unfolding in a singular, unidirectional manner from the moment of the Big Bang to the present and extending into the future. However, in other cosmological models, the nature of time can be strikingly different. For example, in the cyclic or oscillating universe models, time might not have a clear beginning or end, but is instead part of an eternal series of expansions and contractions. Each cycle can be seen as having its own beginning and end, but these are just phases in an infinite sequence, challenging the notion of linear time. The concept of time is further complicated in theories proposing the existence of a multiverse, where an array of universes exists simultaneously but independently. In such scenarios, each universe can have its own distinct timeline, potentially governed by different laws of physics. This raises the question of whether time could flow at different rates or even in different directions in other universes, diverging significantly from our conventional understanding. String theory and theories of quantum gravity also propose intriguing implications for the nature of time. These frameworks suggest that at the most fundamental level, space and time may emerge from more basic, pre-geometric quantum states. In this context, time and space might not be fundamental aspects of the universe, but emergent properties that arise from the behavior of these deeper physical entities. These varying conceptions of time across different cosmological models underscore the profound mysteries that still surround the nature of time. They challenge our understanding and perception of time, pushing us to consider it not as a fixed and universal backdrop against which events unfold, but as a dynamic and deeply integral component of the cosmic fabric itself. As our models and theories evolve, so too will our comprehension of time, potentially revealing deeper truths about the universe and our place within it. The intriguing proposition that our universe might be a simulation, essentially an advanced digital construct operated by a higher intelligence, is a topic that blurs the lines between science fiction and theoretical physics. Philosophical and scientific musings, inspired in part by the rapid advancement of virtual reality and computational power, have led some to speculate about the nature of reality and whether everything we perceive could be an artificial creation. From a scientific standpoint, proving that the universe is a simulation poses significant challenges, primarily because any evidence we might consider as proof would itself be part of the simulation and subject to its rules. Despite these obstacles, theorists have proposed several avenues that could potentially offer clues about our reality. One line of inquiry focuses on the potential for irregularities in the physical constants and laws that govern the universe. Some scientists suggest that, similar to bugs in software, glitches, or unusual precision in mathematical patterns, unexplained phenomena or inconsistencies in the laws of physics could point toward our universe being an artificial construct. Another avenue involves examining the limitations of computing power. If our universe is simulated, it would likely be constrained by the computing resources of its creators. This leads researchers to explore the possibility of a fundamental granularity or resolution limit to space-time, akin to the pixels in a digital image. High-energy experiments that probe the smallest scales of space-time are key in searching for signs that might hint at a computational foundation to our universe. Quantum mechanics also offers intriguing possibilities. The peculiar nature of phenomena like quantum entanglement and the observer effect, whereby the state of a quantum system seems to depend on its measurement, could be interpreted as evidence of underlying algorithmic processes. The challenges of simulating quantum systems on classical computers add weight to this speculation, as inconsistencies or peculiar behaviors in quantum phenomena could potentially indicate a simulated environment. Despite these speculative avenues of investigation, the task of definitively proving that the universe is a simulation is daunting and possibly beyond our reach due to the self-contained nature of such a system. Moreover, the question raises profound philosophical implications about consciousness, free will, and the nature of reality, which further complicate the search for empirical proof. In the absence of concrete evidence, the simulation hypothesis remains a compelling thought experiment and a reminder of the limits of our understanding. It pushes the boundaries of scientific inquiry and philosophical debate, encouraging us to explore the very foundations of reality and our place within it. Theories suggesting the existence of multiple timelines, an idea that finds footing in both science fiction and certain interpretations of quantum mechanics, carry profound philosophical implications that challenge our most fundamental perceptions of reality, causality, and personal identity. At the heart of these theories is the concept that every decision, every quantum event, may spawn a new timeline, resulting in a nearly infinite array of parallel universes where every possible outcome is realized. This notion disrupts the traditional view of time as a linear, singular path, suggesting instead a branching, multiversal fabric where different versions of the universe, and by extension ourselves, coexist simultaneously. The idea of multiple timelines calls into question the nature of reality itself. If countless versions of the universe exist side by side, what does it mean for one's experience of reality? This challenges deterministic views of the universe, positing instead a cosmos where choice and chance play out across an endless tapestry of timelines. It suggests that the universe is not a predestined story unfolding, but a dynamic, interactive plethora of possibilities. The notion of multiple timelines raises intriguing questions about personal identity. If different versions of an individual exist across these timelines, each making different choices and experiencing different outcomes, which one is the true self? This challenges the notion of a singular, consistent identity, suggesting instead that identity is fluid, multidimensional, and contingent upon the timeline one occupies. The ethics of decision-making take on new dimensions within the context of multiple timelines. If every choice spawns a new universe, what responsibility does one have for the outcomes in these parallel realities? This raises complex questions about moral accountability and the consequences of actions not just in our universe, but across the multiverse. The existence of multiple timelines also impacts our understanding of causality and free will. The concept that every possible outcome is realized in some timeline suggests that free will could be an intrinsic part of the universe, with each choice genuinely affecting the course of reality. However, it also raises the question of whether free will can truly exist if every outcome happens somehow, somewhere. In grappling with these questions, theories of multiple timelines invite us to reconsider the very fabric of existence, urging a re-evaluation of our underlying assumptions about time, reality, and our place within the cosmos. By exploring these profound philosophical implications, we enrich our understanding of the universe and ourselves, pushing the boundaries of human thought and inquiry. The realm of theoretical physics, with its exploration of concepts like extra dimensions, entanglement, and the nature of space-time, provides intriguing frameworks that some have speculated could one day offer explanations for phenomena currently deemed paranormal. While mainstream science remains skeptical of paranormal claims, due to the lack of empirical evidence and reproducibility, theoretical physics invites speculation about the unknown with an open mind, considering possibilities that transcend our everyday understanding of reality. Theories proposing extra-spatial dimensions beyond the familiar three, as posited in string theory and other frameworks within high-energy physics, offer a radical expansion of our spatial reality. Some have speculated that these unseen dimensions could account for phenomena perceived as ghosts or apparitions, suggesting that what we interpret as paranormal might be interactions or glimpses into these extra-dimensional spaces that exist alongside our perceptible universe. Known as spooky action at a distance, quantum entanglement describes the observed phenomenon where the state of one particle instantaneously affects the state of another, regardless of the distance separating them. This principle challenges conventional notions of causality and locality, and has led some to ponder if entanglement could explain instances of telepathy or synchronicity, where information appears to be transferred outside the bounds of known physical mechanisms. The role of the observer in determining the outcome of quantum events, a foundational element in the Copenhagen interpretation of quantum mechanics, has led to deep philosophical inquiries about the nature of consciousness and reality. Some speculate that consciousness itself could be deeply intertwined with the fabric of the universe, possibly explaining phenomena like precognition or psychokinesis, where the mind appears to influence physical systems directly. Theoretical constructs like wormholes, based on solutions to Einstein's equations of general relativity, hint at the possibility of shortcuts through spacetime. This concept has been speculated to potentially account for time slips or other anomalies where the linear progression of time appears disrupted. While such notions remain purely speculative and face significant theoretical and practical hurdles, they offer intriguing possibilities for reinterpreting experiences labeled as paranormal through the lens of advanced physics. It's important to emphasize that these speculations are not endorsed as scientific explanations for paranormal phenomena by the mainstream scientific community. Currently, they remain intriguing intersections of theoretical physics and human curiosity about the unexplained. The rigorous standards of evidence and reproducibility in science necessitate caution in drawing conclusions from these speculations. However, the history of science is replete with instances where today's heresies became tomorrow's truths, underscoring the value of keeping an open yet critically discerning mind toward the unknown. In the vast and enigmatic field of cosmology, the boundaries of human knowledge are continually pushed forward by technological advancements and theoretical breakthroughs, yet several profound questions remain that challenge our current understanding and capabilities. Despite constituting roughly 95% of the total mass energy content of the universe, dark matter and dark energy remain largely mysterious. The inability to directly detect dark matter particles or fully explain the accelerating expansion of the universe attributed to dark energy highlights significant gaps in our understanding of the fundamental constituents of the cosmos. The Big Bang Theory provides a robust framework for understanding the evolution of the universe from a hot, dense state. However, the exact nature of the singularity from which the universe is thought to have emerged, and the conditions existing at that moment, elude our current understanding. Quantum effects are expected to dominate, yet a complete theory of quantum gravity, necessary to describe these conditions, is still lacking. While current observations suggest an ever-expanding universe, the ultimate fate of the cosmos depends on factors such as the true nature of dark energy and possible changes in the laws of physics over vast timescales. Whether the universe will continue to expand indefinitely, resulting in a big freeze, or eventually collapse in a big crunch, or experience some other fate, remains an open question. The concept of a multiverse, where our universe is just one of many, potentially with different physical laws and constants, opens up vast realms of possibility, but also presents significant challenges to verification. The question of whether we can obtain empirical evidence for the existence of other universes, or if the multiverse hypothesis will remain in the realm of philosophical speculation, marks a stark boundary in cosmological inquiry. The puzzle of what happens to information that falls into a black hole, a question with profound implications for the nature of reality and physics itself, remains unresolved. Theoretical work, including Stephen Hawking's proposals regarding Hawking radiation, points to deeper connections between gravity, quantum mechanics, and thermodynamics, suggesting that foundational revisions to our understanding of physics may be required. These boundaries of human knowledge in cosmology underscore the inherent limitations of our current theories and technologies, while offering a glimpse into the profound mysteries that the universe holds. Each represents not just an edge of our understanding, but a frontier for future exploration, promising that the journey of discovery in cosmology is far from complete. The possibility of undiscovered forces of nature presents a tantalizing frontier in physics, holding the potential to profoundly redefine our understanding of the universe. Throughout history, the discovery of new forces, such as electromagnetism and the weak and strong nuclear forces, has revolutionized physics, leading to paradigm shifts in how we understand the cosmos and its fundamental laws. Today, several hints suggest that our current model of physics, while incredibly successful, might not be the complete picture. For instance, the mysteries surrounding dark matter and dark energy, which together constitute a significant majority of the universe's mass energy content, hint at the possibility of forces or particles beyond those described by the standard model of particle physics. The inability of the standard model to incorporate gravity or explain the imbalance of matter and antimatter in the universe further underscores potential gaps in our understanding. The search for new forces often involves looking for anomalies or deviations in expected physical behavior, both at the cosmic scale and in controlled environments, such as particle accelerators. For example, discrepancies in the behavior of particles compared to standard model predictions could indicate the influence of forces beyond those currently known. Similarly, unexplained phenomena in astrophysical observations could hint at new forces acting over large distances or at dark matter interactions not accounted for by gravity alone. The detection of a new fundamental force would necessitate a significant revision of the standard model, possibly leading to a more unified theory of nature that encompasses all four known forces and any newly discovered ones. Such a theory could resolve long-standing puzzles in physics and open new avenues of research, with implications ranging from the nature of the universe's formation to technological innovations based on novel principles of physics. In the pursuit of these undiscovered forces, physicists employ both precision measurements of known phenomena and exploratory experiments that probe the boundaries of current theories. The endeavor is as much about testing the limits of our existing models as it is about discovering new aspects of nature, reflecting the dynamic and ever-evolving nature of scientific inquiry. The potential discovery of new forces of nature stands as a testament to the profound depth and complexity of the universe, inviting us to continually expand the horizons of human knowledge. Balancing scientific speculation with empirical science in cosmology involves navigating the fine line between imagination and evidence, a task that is both challenging and essential for the advancement of the field. Cosmology, by its nature, deals with phenomena that are often at the limits of human observation and comprehension, necessitating a blend of theoretical innovation and rigorous empirical validation. Scientific speculation plays a crucial role in generating hypotheses and theoretical models that push the boundaries of current understanding. These speculative ideas, while grounded in established physics, often extend beyond observable reality to propose new concepts, such as extra dimensions, multiverses, or unknown forms of matter and energy. The creativity and insight into these speculations stimulate progress, driving the search for new empirical evidence. The ultimate test of any speculative theory in cosmology lies in empirical validation through observation and experimentation. Advances in technology, such as more powerful telescopes, particle accelerators, and space probes, provide the means to observe the universe with ever greater precision and breadth. The search for empirical evidence requires careful design of experiments and observations to test the predictions of speculative theories, with a willingness to revise or abandon these theories based on the results. The balance between speculation and empirical science is also maintained through the peer review process and ongoing discourse within the scientific community. Peer review ensures that speculative theories are rigorously evaluated for their scientific merits, coherence with established knowledge, and potential for empirical testing. Scientific discourse, including debates and collaborative efforts, fosters a healthy skepticism and critical thinking, essential for refining theories and guiding the search for evidence. The interplay between speculation and empirical science is inherently iterative. Speculative theories that are supported by empirical evidence become integrated into the broader theoretical framework of cosmology, while those that are contradicted by evidence are modified or discarded. This iterative process of hypothesis, testing, and refinement is fundamental to the scientific method, allowing cosmology to advance in a manner that is both imaginative and anchored in reality. In summary, balancing scientific speculation with empirical science in cosmology requires a symbiotic relationship between imaginative theoretical work and rigorous empirical investigation. This balance ensures that cosmology progresses as a robust scientific discipline, continually expanding our understanding of the universe while grounded in observable reality. Consciousness, while primarily a focus of philosophy, psychology, and neuroscience, intriguingly intersects with theories about the universe in several areas of theoretical physics and cosmology. The involvement of consciousness in these theories ranges from the interpretation of fundamental physics principles to speculative ideas about the nature of reality itself. Perhaps the most well-discussed intersection of consciousness with theories about the universe comes from the realm of quantum mechanics. The observer effect, particularly in the context of the double-slit experiment, suggests that the act of observation can affect the outcome of a quantum event. This has led to various interpretations about the role of consciousness in the measurement process, with some physicists speculating that consciousness itself may play a fundamental role in determining the state of quantum systems. The anthropic principle posits that the fundamental constants and laws of the universe are finely tuned in a way that allows for the existence of life, and by extension, conscious observers. This principle raises questions about the relationship between the cosmos and the presence of consciousness within it, suggesting that the universe may in some sense be designed to foster conscious life. There are different formulations of the anthropic principle, from weak observations about the conditions necessary for life to stronger, more controversial suggestions that the universe is somehow predisposed towards consciousness. Some speculative theories go further, proposing that consciousness might be a fundamental aspect of the universe. Panpsychism, for example, posits that consciousness is a basic property of all matter, suggesting a universe where the line between conscious and unconscious matter is blurred. Similarly, the idea of a participatory universe, as put forward by physicist John Archibald Wheeler, suggests that reality is co-created by physical processes and conscious observers, blurring the distinction between observer and observed. In recent times, theories that conceptualize the universe as a manifestation of information processing have also intersected with notions of consciousness. These perspectives suggest that consciousness could emerge from the complex information processing carried out by the universe itself, leading to hypotheses where the cosmos could be understood as a vast computational entity with consciousness arising as a natural byproduct. While the inclusion of consciousness in theories about the universe is highly speculative and remains a topic of vigorous debate, it reflects an enduring interest in understanding the deeper nature of reality. These explorations, bridging science and philosophy, underscore the profound mystery of consciousness and its potential relevance to the fundamental workings of the cosmos. As our understanding of both consciousness and the universe deepens, the interplay between these domains may illuminate some of the most profound questions about existence. The quest to understand the universe is one of humanity's most enduring endeavors, but it is a journey marked by inherent limits shaped by the nature of scientific inquiry, the capabilities of our technologies, and the fundamental properties of the universe itself. These ultimate limits frame the horizon of our understanding, delineating what might forever lie beyond our grasp. One fundamental limit is imposed by the speed of light. The finite speed at which light travels means that there is a boundary to the observable universe. Regions beyond this cosmic horizon are inaccessible to us because their light has not had time to reach us since the beginning of the universe. This limitation confines our direct observational reach, potentially leaving aspects of the universe forever hidden. At the microscopic scale, the Heisenberg uncertainty principle delineates intrinsic limits to the precision with which certain pairs of physical properties, like position and momentum, can be known. This quantum uncertainty introduces a fundamental fuzziness to our understanding of the universe at the smallest scales, affecting our grasp of the initial conditions of the universe and the exact state of quantum systems. The sheer complexity of the universe presents another limit. Even with advances in computational power, modeling the universe in its full complexity, accounting for every particle, force, and interaction over the expanse of cosmic time, is an insurmountable challenge. Computational limits also constrain our ability to simulate complex phenomena, from the formation of galaxies to the nuances of climate on potentially habitable exoplanets. What do you think exists out there in the universe? Are we truly alone in the universe, or do distant civilizations exist? Let us know your thoughts in the comments below. Thanks for watching.